For those who already joined, hi, we'll wait one more minute and then we'll start, okay? Okay, we'll start in half a minute as people are joining in very quickly. Numbers growing, so we'll give it half more minute and then I will start with opening. All right, let me start. I'm not the important part of the workshop anyway. So anyways, welcome everybody to our workshop on deep internal learning. We're 5 organizers, Tamar, Rott, Shaham, and Michaeli from the Technion, Assaf, Shocher, and myself from the Weizmann Institute, and Tali Dekel from Google, who will shortly be joining Weizmann, is actually right now on the plane from Boston to Tel Aviv, and therefore cannot join the workshop, but we're all really happy to have you. So what is this workshop all about? Well, what is deep internal learning? Well, deep learning is typically divided into 2 phases, a training phase and a separate inference phase. In the training phase, we typically rely on lots and lots of training examples. And these networks, once trained, are fixed and are applicable only to the type of data they were trained on. Such networks cannot exploit nor adapt themselves to the internal statistics of a new test datum. On the other hand, there is this whole thing of internal statistics of a single natural image or a single natural video, and it has long been recognized as a very powerful tool in computer vision. Exploiting the internal redundancy inside a single image or a single natural video often allows us to do completely complex inference tasks in a totally unsupervised way. We refer to this as internal learning. Now, internal learning, which has been going on for 2 decades or so, regardless of whether it's deep or not deep, requires no training examples besides the test input. It allows training, and in the past few years, it also gained interest in the deep learning community. It allows training deep networks on a single training example. And surprisingly, these deep networks that are trained on a single test datum often achieve state-of-the-art performance while being significantly more flexible than externally trained networks. And the goal of this workshop is to present the main ideas and recent advances in deep internal learning, which is gaining more and more interest in the community. So what's in our program? We have 5 keynote talks with live question and answers. The 3 keynote speakers are invited speakers. These are Andrea, Vedaldi, Alexei Efros, and Barron. Each one of them will talk about the different aspects of internal learning. We also have 2 additional talks by the organizers, since we have a thing or 2 to say about internal learning. One talk will be by Assaf, Shocher, and myself. It will be given in the first session, and another joint talk will be given by Michaeli and Tamar, Shaham, which will be given in the second session. In addition to these 5 long talks, we also have several excellent short orals with live question and answers. The short orals have been pre-recorded and can be found on our website. And by the way, we had lots of submissions of pre-recorded short orals, all of them related to internal learning. We selected only the best ones, and we selected a few of them further to present, to play them live in the workshop, and they're pre-recorded videos with a live question and answer session. But you can find all these pre-recorded videos, which are all excellent, on our workshop website. The keynote talks have not been pre-recorded. These will be given live during the workshop, but they will be recorded. I hope Tamar is already recording right now everything, and they will be recorded during the workshop, and we will post them on our workshop website immediately afterwards. So what does this, what's the schedule look like? All the time, we have a 5-hour workshop. All the times you see here are UTC+1, which is actually Glasgow time or London time, whichever is more convenient for you to think about. The 5 keynote talks will be spread across these 3 sessions. 2 will be given in the first session by Andrea, Vedaldi, and Tomer, Michaeli, and myself. This, one keynote talk will be given in the second session by Tomer, Michaeli, and Tamar, Rott, Shaham. And the first, and then 2 more invited talks in the last session by John Barron and Alexei Efros. And the short orals will also be spread across the 3 sessions. We will have 3 short orals in the first session, 2 in the second, 5 in the second, and 3 in the third. And any questions you have, we will have live Q&A sessions at the end of the long talks and after every 3 or 2 short orals. So any questions you have, please type them in the chat and we will be reading them to the speakers in the Q&A session. So without any further ado, let's move to our first speaker, Andrea Vedaldi, and let me actually pass the stick on to Tomer Michaeli, who will chair the first session and also present Andrea. So please.
Okay, great. So our first keynote for today is going to be given by Andrea Vedaldi, who I think needs no introduction in our community. Well, for one thing, he's a program chair in the ECCV, but anyway, Andrea is an associate professor at Oxford, UK, and a research scientist at Facebook AI Research. He's made many important contributions to computer vision, which I'll not list. I'll just say that in the context of our workshop, he's co-author of one of the interesting papers on extracting information from a single image, which is the deep image prior. He also received quite a few awards, including a recent Best Paper Award in CVPR 20. And in this talk, he's going to tell us about deep image priors. So Andrea, the stage is yours. Andrea, you're muted.
Hi. Okay, I'm gonna say that again. Thank you for the introduction. And I'm gonna try to share my screen now. Yep, okay, I think like that. And you should be able to see my presentation, I hope. Or not. Okay, let me try that again. Interesting. You can still see myself though, right? Or me. Okay, this was working before, so I expect this to work again. Does that work?
Yes.
Okay, excellent. All right, yeah, so what I would like to talk to you about today are these deep priors. A lot of what I'm going to say today is not actually new, came out a few years ago. So this is going to be as much as retrospective as also some comments on our prior work. But I'm also going to tell you about something a little bit more recent too. All right, so I would like to start from a very, very simple picture. So this is what we generally do. Whoops, that didn't really work. Yeah, okay. What we generally do when we consider a deep network and want to learn, and so really this is a model for most of what we do in machine learning when it comes to supervised learning. So of course, our goal is to learn a function, which we're going to do with a symbol phi. And this function goes from some input, could be an image or a video, and then it does something maybe complicated. And then at the other end of the diagram, it spits out an answer that as something that is of interest to you. In this case, it could be the label of the image, okay? So that's the setup. The question is then, how do we actually find this function phi in such a way that it solves the problem we want? So, this is a learning problem, a learning process really, but a good way of looking at that is through sets of functions. So this would be a representation of the space of all possible functions that go from your data to a label, all right? This is a very, very large set. And there is a specific function here, one element, which is the one you really want. Okay, now the task of learning is to find within this set of functions, the one that actually works well for you. So you want to pick a good function. So what does that mean? Well, so this would be the subset of functions that actually work well on your test data. So it means that you take one of those guys, you apply it to your problem at test time. So when you actually want to use this for an application and it works well. For example, it classifies images with a low error rate. Now, the problem, of course, is that you don't really know what the test data is when you train the function you're designing. This is only gonna come in the future. So as a designer of the function, what you have to work with is the trained data set, of course. So this is the space of functions that actually do well on the training data. But the problem is that training and test data are not the same. So what this means is that while there is usually an intersection between what works well on the test data and what works well on the training data, of course, the intersection is not a complete overlap. So you're interested in picking a function in this intersection between the two sets. But the problem is that when you train your model, you do not have knowledge of the green set, you only know about the blue set. So what are you gonna do? Well, generally what we do in machine learning is to restrict our attention to a space of function, which is much, much smaller than the one that it would be possible to consider otherwise. So these are denoted here as searchable functions. And so what I would like to focus my attention on in the rest of the talk is not so much the training and test data, but is really what is the space of useful functions that we can search for in order to be successful as finding something that actually works well on our test data eventually, all right? So this talk is gonna be about what is the nature of this set, the set of searchable functions. Now, when we consider deep learning, or we consider, generally speaking, any machine learning model that, again, we train in a supervised manner, what happens is that, first of all, we're gonna pick a set or class of functions, for example, possible neural networks. Within that, we're gonna pick a particular structure for the function, or an architecture. Could be, for example, AlexNet. So this is gonna be this model here. But that's not enough. That's still a space of functions because you didn't say yet what are the values of the parameters of the function. So this is in particular a parametric set, all right? And what we're gonna do is we're gonna choose an architecture, and then within that, we're gonna try to find the parameters of the model that make this work well, all right? So we want to find within this parametric set a function that works well by finding the correct parameters for it. Now, and this is the key message here. So by just choosing an architecture, for example, choosing AlexNet, or more in general, choosing convolutional neural networks of different kinds, well, that is equivalent to adding some information to your learning process, okay? So just the act of choosing an architecture, even before you start looking at the value of your parameters, well, that amounts to setting or injecting in your learning process some prior knowledge. So when we introduced this deep image prior, what we really meant is the fact that by choosing architecture, then you're choosing to inject in your learning process some prior knowledge. And the interesting thing is to clarify or try to explore what exactly this prior knowledge amounts to, because it's very implicit. You're just choosing a deep neural network architecture, say AlexNet, and then that comes with some prior knowledge, just this act of choice, but you don't really know what it is. So deep image prior is about trying to tease this out a little bit. So again, this is another way of looking at the same story. So we have a learning process here in this box that will spit out a network, a trained model, and then that's going to be evaluated on a test set, all right? So now, inside, in the learning box, this box to the left, you're going to inject some information. So first of all, you're going to have some training samples. Could be, say, 1 million images in ImageNet, maybe 1 billion Instagram images, usually something very large when it comes to deep learning, okay? Very often this data is also labeled. So not only you have images or videos, but you also have labels for them, okay? Then typically you do something actually to make the data even larger. So you augment it. For example, you can apply some random crops when it comes to image classification because you want your classification function to be invariant to crops. And then you also make a choice of an architecture to learn, right? So these three things plus a few more is what actually gets into inside this box and allows the box, which is the learning process, learning algorithm, to actually spit out a network for you. Eventually, here comes a test sample. Usually you have many test samples, but for the purpose of evaluation, you can consider one of them at a time. So you observe a single test sample, you evaluate your network on that, and usually you profit. Profit here means that the network solves an interesting problem, such as, for example, classifying an image that you have here, okay? Now, this is a standard supervised learning pipeline. So what I want to focus on again here is just the network architecture. So what I'm gonna do is I'm gonna look at this in a different manner. So I'm gonna drop the other two sources of information. So training data augmentations for now. And I'm only going to focus on the choice of deep neural network architecture and a single test sample. And I'm gonna try to profit from the combination of these two things alone, all right? So there is no training per se anymore, or if there is any training, it happens only based on a single tested sample you provide, okay? So this really allows me to put the focus on the information which is already encoded by just choosing a particular architecture. All right, so how can I do this in practice? Well, I'm gonna do that in a particular context, which is image generation. So what is a generator network? This is a network, which is usually a convolution neural network. It takes as input some noise, a noise vector, has some parameters W, and then through a set of convolutional layers, maybe some convolutional layers as well, it produces as output an image X, all right? And I call this function psi to distinguish it from the generator that I had before, which was conveniently called phi instead, all right? Now what I'm gonna do is gonna take this, which is usually learned from training data, and look at that instead as a parameterization of my image. So this is the same, I just have rewritten slightly the notation in such a way that now inside the box I have my network as well as the value of the noise which is provided as input to the network. I'm gonna freeze that to some random numbers, but these are not touched anymore. And then what I'm gonna do is gonna change W and see what image is being produced by the network, okay? So what this means is that now the network is just a parameterization of my image. There's a function psi that goes from the parameters of the network to the image X, okay? So now I have a way of parameterizing an image through the choice of a deep neural network. And this is entirely handcrafted because the parameters have not been learned, all right? This is purely done by manual design, if you like. Now, next, what I want to do is try to find the parameters that generate a particular image. So here is my image. Of course, this is a natural image that I've downloaded from the internet, and I don't know which are the values of the parameters W that actually correspond to this particular image. So how do I find them? Well, I just set this up as an optimization problem. So I take my image X, I set W to some random numbers initially, and then I generate an image corresponding to these random numbers, which initially will look like garbage. And then what I do is I compare my image X to this stuff which is being produced by my network. For example, just measuring the L2 distance between these two things, and then I backpropagate to the parameters in order to find W that generates my image. Okay, so it's just like an optimization process, which is very, very similar to learning your parameters of your network. Here, instead, the interpretation is that we are finding the parameters of this image where the parameterization function is given by the network, okay? All right. Now, why is this useful? Well, because it reveals some interesting properties of your architecture. So what you see in this graph is the convergence speed of this process, right? So what you see here is iterations on the x-axis. And on the y-axis, what you see is the L2 distance between what's being generated and, excuse me, and what is actually my target image that I want to reconstruct. And over time, you're gonna see that the L2 error decreases because as you do more iterations, then your parameters become better and they correspond more directly to the image you want to reproduce. Now, what it comes out to be the case is that the convergence speed or the ease in which you can solve this problem strongly depends on the nature of the image you put in. So if you put in a natural image like this, the convergence speed is rather fast. But as you try to reconstruct images which look more and more, or less and less natural, more and more noisy, then it turns out that it's actually very, very hard for your network to find parameters that actually give you back this image. Okay? Now, what this means is that in a certain sense, this parameterization we have found by just picking a network has a very low impedance to signal. So it likes to reconstruct naturally looking images, but it has a very high impedance to noise. It means that it doesn't really like to reconstruct stuff which looks noisy, okay? We can use this to actually solve some problems which are actually useful. For example, suppose I want to do in painting. So in this case, what it means is that my input is an image for which only some of the pixels are revealed, all right? So what I can do is I can set this problem as I did before, an optimization. So I look for values of W that reconstruct my image, trying to match the value of the pixels that I know. But I also have a mask here, M, in the formulation that tells me that I won't pay a cost for trying to match the pixel that I don't know. So essentially what this means is to find the parameters of the network that generate only the visible pixels, and then the network will also produce a value for the remaining pixels, all right? And that's gonna give me a completion of the image, okay? And so this is the sort of results you can get with this. So here, this is a convolutional coding method, which is, was at the time at least, state-of-the-art method for imaging painting. And this is what you see by training, by not training, but actually by optimizing a single network on a single test image, what sort of in-painting results you can get. And they're very comparable, and perhaps this is actually slightly sharper, okay? Here's some harder example. So that example was kind of easy because it was dropping pixels randomly from the image. But suppose I erase an entire patch. Now this is harder because, you know, it seems like farther away from a simple interpolation problem and more something that would require some semantic in order to understand what's actually goes in here, all right? So you could solve this by training a network to perform in-painting, but even if you don't do that, and you just use this deep image prior trick, if you like, then without any training, just giving this as data, right, just the test, that essentially the test image, where you want to apply this to, then this is the in-painting result that you get, which is pretty reasonable, all right? But what's happening here is that the network somehow knows how to complete the missing bit here because it can look at similar patches around the image, okay? But it's very effective at doing that, even though the network was not really designed to solve this problem. It just happens to be a good prior for in-painting. And here's a even more challenging example. So here you can see that lots of bits in this image have been removed. And here you can see the results that we can get, again, without having any specific training for a network for in-painting. Just out of the box, this is what the network actually does, okay? All right, now I would like to discuss a few more applications of this. So one of them is as follows. So suppose I have a network. Now this one, it has been trained. So this is say AlexNet that was trained as an encoder for solving image classification in ImageNet, say. So as input I have an image, as output I have a label, and these parameters are now known to me because they have been trained on ImageNet, but I want to study what has actually been learned by the network. So what I can do is I can look at this as an encoder. So I take the first couple of layers of AlexNet, I call them phi, yeah? And then I look at this as a function that maps the image onto some features. So what I'm doing really is I'm looking at a subset of my AlexNet network as an encoding network that goes from images to codes, okay? Now I want to study this encoding function, and I'm gonna go back in a minute on why this is relevant to deep image prior. But so bear with me for now. So this is actually learned, right? So what I want to do is I have this encoding function, I want to study it. So one way of doing that is try to find out which images correspond to a given code. So if I take an image X1 and I produce a code as output, in general, I will have many other images that happen to produce the same output as well. So the network is a many-to-one function, if you like, all right? Now, what I can do is I can try to look for which images in input sets correspond to the same code. And that's interesting because that means that these images are indistinguishable from the viewpoint of your network. Or in other words, this is a way of visualizing the invariances that the network has learned, okay? So what I want to do is to find this blue set here, which is called the image of this particular code. And I'm not going to try to do that exhaustively, but I'm going to try to do that empirically so we can generate some visualizations, okay? So what this means is that I'm going to start from an image, X0, for example, this black swan. I'm going to encode it using my AlexNet up to a certain depth in my deep neural network architecture. And then I'm going to take a random image and I'm going to try to optimize it in such a way that the code of what I get here and the code of this particular image here are identical. So the process of optimization will look something like this, okay? By the end of the optimization, I will have found an image X, which generally is not the same as X0, but they happen to have the exact same code as output, okay? So they're equivalent from the viewpoint of the network. Now, this is the crucial bit. So if you do this in general, you will get some reconstruction which doesn't look very good. The reason is that the network was trained to operate on natural looking images. It was not trained to operate on random images. And for those random images, we'll produce random codes, including codes that happen to match the one you want. So when you do this inversion process, you would like, if possible, to restrict yourself to images which not only invert the code, but also are naturally looking, all right? So ideally, we would like to do an inversion based on natural images. That's actually very hard. So what we're gonna try to do is to use a prior to tell us which images are natural enough and then doing the inversion there, okay? So this is what I call here a pseudo-natural image, all right? And this is gonna be not as natural as it should be if you were actually able to characterize the prior natural images properly, but it's gonna be better than actually not posing any prior at all. And it will give us a result which is more meaningful and more interpretable, all right? Now, I'm gonna go this slide very, very quickly, but suffice to say that this is a description of the process of inversion. So here you see at the top your AlexNet you want to invert, and this stuff here in the box is your inversion process. And the trick here is that I'm gonna use my deep image prior, which has no training at all, all right? That's very important because that's not gonna bias through training data, my inversion process. Nevertheless, I'm gonna use that as a way of regularizing the reconstruction to make it look like it's more natural. Again, just purely by the computational prior, which is embodied in the network. So it's the same process of optimization described before. But now the image which is being reconstructed is going to be parameterized by my deep image prior, and as a consequence, it's going to be more regular, more naturally looking. Now I'm going to apply this to AlexNet. So you see here layers of it. And I'm going to start with the inversion of COM1. So it means that I take my input image, I pass it through COM1, I get a code, and then go back. And you can see that the inversion looks pretty much like an identity. But as I go deeper down in my architecture, what you see is that the reconstruction, so here we have maybe COM3 or so, the reconstruction looks less sharp. What this means is that these are invariances that are learned by the network. So the network doesn't care if your image looks like a sharp monkey or a monkey where the bits are a little bit dislodged. For it, from the viewpoint of the code, which is being computed, is the same, okay? And if I go deeper down, then you can see that as soon as you start looking at fully connected layers, where the spatial code, the spatial part of the code is essentially lost, then you can still reconstruct a monkey image, but for example, now you see 3 eyes, right? Again, what is interesting here is that this monkey image and the original monkey image, from the viewpoint of whatever happens after FC6 in AlexNet, they are exactly identical or nearly identical from the point of the network. So the network is not able to distinguish between these two. And as you go deeper down, you see that the effect is even more emphasized. Okay. This is a summary slides where you can see the entire progression. And here is another interesting thing I wanted to mention. So if you look at the very last layer of AlexNet here, FC8, that's a code for 1,000 different ImageNet classes. And in theory, you know, the code here should only memorize your actual class label. You should not memorize details about the appearance. Here we're reconstructing frames of a video individually. That's why you see them flicker, because there is no temporal consistency to this process. And you can see that as you go deeper down the network, there is more flicker, which corresponds to the fact that there is more invariances coded up by your network, okay? Now, what we can do is observe what happens at the last level though. So again, remember that this in theory is just a code for the class memorized by, recognized by the network. But if you see what happens here, you really do see that there is some appearance-specific information which is still lingers on, all right? Now, when we discovered that, we were actually very surprised because again, in theory, at this level in the network, there should be no more appearance information. There should only be a class information, but actually this is not the case. Okay, so that was interesting to discover. Okay, so I guess I still have a couple of minutes. So I'm gonna go to the last part of the talk, which is gonna go beyond deep image prior, actually. But it's similar in philosophy. So what we want to achieve is to look at you know, how much training data we really do need to be able to learn properties in networks, okay? So of course, the standard approach is supervised learning, in which we have a large data set with a lot of labels for it. And then we can train, for example, a segmentation network. And as we all know in division, one problem is that getting this label data is actually very expensive. So what we would like to do in self-supervised learning or unsupervised learning is to be able to get a network that, you know, solves a task of interest, but it does that without having access to labels, right? Only using a raw training data. So looking at the scheme I had before, in self-supervised learning, what we do is we're gonna take, in particular, our larger data set of images like ImageNet or something else, but without labels. We can have a pretext learning task, for example, colorization or rotation estimation, that does not require us to provide labels to it. That's going to spit out a model, a pre-trained model, that is not directly useful for solving a problem I really want to solve, but presumably now this network, which has been pre-trained, is close enough to solving the problem I want, that then I can still supervise learning, but with a much smaller training set now. This still has label, but it's much smaller, so it's cheap to get. And then I can get still a model that solves my problem with sufficient accuracy. So most of the work in theory should be done by this pre-training process, which uses a very large training set which is fine to get because we don't need labels for it. So we can just randomly download images from the internet, which is really cheap. Okay. All right, and then I get a final model that presumably works well. All right, so what goes into this box, pretext learning? Well, of course, you get a large train set without labels. Then you get a choice of pretext tasks, which is, there is an whole set of papers on that. That is actually very interesting. But then something else goes into this box. Usually there is a process of data augmentation, for example, applying random transformation to your images. And you're gonna see that all pretext tasks that actually work well do use a form of data augmentation usually, okay? And then there is a choice of neural network architecture, which is my deep prior. So I'd already discussed that. So what I'm gonna focus on now is the role of augmentations and whether it's actually important or not to have a very large training set for pretext learning, okay? In particular, what I'm gonna do is gonna try to apply these self-supervised formulations with the same setting as usual, but rather than using a very large training set of images, which are unlabeled, I'm gonna just use one image, okay? That might sound bizarre, but the point of this is to verify whether this pretext learning box can actually extract non-trivial information from whatever unlabeled data set I put in here, okay? Particularly in our paper, we have considered 3 images, and each one of them is trained independently. So we repeat the experiment 3 times, image A, image B, image C. Each one of those is its own data set, okay? And then what we do is we take that and we use a off-the-shelf self-supervised learning method to try to learn a representation out of it. We consider 3, deep cluster, Rott, and BiGAN, and big BiGAN as well. The reason is that this was what was state-of-the-art at the time. Now these methods are actually rather old, and there is a new class of methods for self-supervised learning which are much better. So the conclusions that I'm going to show you in a minute might not directly apply to what has come out since. So these experiments would need to be redone now. Okay, but for what was available 6 months ago, these were the results. Again, so the point is we compare training using 1.2 million images from ImageNet with or without labels, to just choosing one image and generating 1.2 crops of that image. So we use data augmentation, very heavy data augmentation, to just take one image and create a data set to train our self-supervised learning method on, all right? And so what happens here is, yeah, okay, this is just an explanation of what you just said. So what do we learn here? So what the first thing is that we want to understand is how much information is contained in a single image. And second is whether self-supervised learning methods are able to extract more information if more than one image is actually provided. All right. So this is the result of doing this. If you look at the COM1 filters in AlexNet, so this is 1.2 million images in ImageNet, and this is what you get with these different methods using only a single image and without labels. All right, and you can see that the filters they look alike quite a bit. All right, so this is just an illustration, but quantitatively speaking, let's have a look at what happens here. So now what they're going to do is they're going to pre-train using different methods, the first couple of layers in AlexNet, from COM1 to COM5. They're going to freeze those layers, and then use those features to solve ImageNet classification using a linear classifier. So this is called the linear probe method, all right? And the idea here is that you're going to do well only if your features are actually good. And I'm going to compare different kinds of features. I'm going to compare random features where there is no training at all, not even, so I just take a AlexNet and plug in random numbers and I get some numbers out and I use those for classification. And I'm gonna use one single image and unsupervised learning to learn the representation. I'm gonna use 1.2 million images and unsupervised learning, so no labels. And then I'm also going to compare to the case in which I do have labels and 1.2 million labeled images, okay? That's the sort of performance that you get if you use random numbers. So you can see that as you go deeper down your network, so should have in principle access to more informative features, this doesn't really help. So across the board, you get pretty poor performance when you train these linear probes, about 10% accuracy, okay? Now what happens is that if you take a single unsupervised image and you train with self-supervision, all these numbers go up quite a bit, okay? Which is already very interesting. So this is done by training a single image, okay? 1.2 million augmentation of that, but a single image. Well, now what happens if instead of having one image, you have 1 million images? Well, things go up a little bit, but not very much. Okay, that was very interesting. So COM1 is the same. COM2 basically is the same as well. COM3, which is a bit more abstract, I would say, but there is a benefit from looking at images, but it's not dramatic. And then as you go deeper down, then the benefit is larger, but your overall performance also goes down. At least this was true for this old school slightly order self-supervised learning methods, okay? And what happens if you do a 1.2 million supervised? Well, that was actually working quite a bit better at the time, okay? So you can see here that the gap is actually quite large. So it means is that it's not enough to provide images. When you have only 1.2 millions, only, quote unquote, labels are still very important even for those methods. The other message here is that even if you just use a single one plus segmentation, then that gives you, in some cases, most of the performance we get from this process of supervision, which means that really what the network is learning is to process images in a transformation invariant manner, but it's not necessarily learning about high-level semantics. Again, with the caveat, this might be completely different. This latest class of self-supervised learning methods that would actually perform much better than this. Okay, so the conclusions are, first of all, maybe that's obvious, but there is a very strong prior in choosing architecture, and that's, I think, shown quite amazingly by the deep image prior. You can solve problems like in painting by using not training data at all, just a single test image. The other thing that these networks are doing, at least for what concerns image classification, first of all, seems to be just being invariant to image transformations, as well as being distinctive in some sense. Otherwise, that would be trivial, all right? And there is still a bit of a question mark, which requires more study, of whether this new class of self-supervised learning methods are actually better able to extract higher level semantics from your unsupervised level training set. Okay, so that's all I had, and maybe there's a little bit of time for questions, or maybe not.
Yeah, great. Thanks for the great talk. I think we have a few questions. Okay, there is a question. Does that mean that the NAS can be done on prior tests?
NAS, meaning, sorry, what was that?
NAS.
Oh, neural network architecture search, you mean? I don't know. So it shows that there is a gap between self-supervised learning and supervised learning, I think. So that gap, so when you choose an architecture using neural architecture search, yeah, that would be, that gap would still exist. So it's not obvious that, yeah, I would take this conclusion with a grain of salt. So maybe it does suggest that even without training data, you can test to some extent the performance of a network without lengthening process. But what we didn't show is how closely correlated is the performance when you train without training images. So when you use a network without training images, and when you actually do want to train from 1.2 million images in ImageNet. So there may be a gap or difference in which architecture work better in one case and which architectures work better in the other case. So if your NAS is done for the second, with the second goal in mind, maybe this won't be so useful.
Okay, I don't see any other questions. If you have questions, please write them in the Q&A chat. I have one question about the deep image prior. You said that the deep image, I mean, the architecture itself prefers certain images over others, like natural images over noise, but you also showed that you can do, for example, super resolution with that. And in super resolution, it seems like it prefers sharp edges over blurry edges or something like that. Do you have any intuition about that?
Yeah, so this is something that you can observe in a neural network when they're used for generation, I think. So differently from, say, linear models, you will notice that they tend to have sharper edges in my experience. Now, I'm not really too much of an expert in generation, despite the fact that I've worked on this a bit in the past. But I think if you see maybe also some recent works by Bolezu, where he was showing what kind of images can be learned by a GAN. For example, showing whether you can train a GAN on some random images and then reconstruct people or not. Well, one thing you will notice that as part of those experiments, it was showing the effect of activating or not individual neurons in the reconstruction process. And that would tend to essentially add an entire region which was overlaid in a sharp manner to what was there before, almost like a layer-wise model. So I think this happens because of the nonlinearities like ReLU in your model, and that favors the appearance of the build-up of sharp edges where you have interactive regions that can switch on and off in your model, okay? So I think it's natural for this model to try to get sharp edges because they are a bit layer-wise like.
Okay, I think we need to move on to the next talk. So thanks again for the great talk.
Like,
Okay, so our next keynote talk is going to be a joint keynote by Michal Irani and Assaf Shocher from the Weizmann Institute of Science. Michal is a professor at the Weizmann Institute. She's made many fundamental contributions to computer vision, for which she received many awards. These include the ECCV Best Paper Awards in 2000 and 2002, the Honorable Mention for the Mar Prize in 2001 and 2005, the Helmholtz Test of Time Award in 2017, and the Landau Prize in 2020. Assaf Shocher is a PhD candidate under the supervision of Michal, and together they were the first actually to explore some of the most brilliant ways of using deep learning on a single image. And in this talk, you're going to tell us about exactly that. So the talk is about deep internal learning, deep learning with 0 examples.
Thank you, Tamar. Can you hear me? Okay, yeah. So Assaf and I will give a joint talk about the deep internal learning. We will be passing the stick from one to the other several times throughout the talk, and we hope you will enjoy it. So what do we mean by deep internal learning? What we mean by that is how we can train a deep network in a totally unsupervised way without ever having seen any prior examples by training on a single image, the test image alone. Why is this interesting? Well, we're all used to external learning. That is to say, we train a network for days or hours or whatever on lots of prior data. Then we fix the network, and then we apply it to new test data as it comes along. And this does, of course, amazingly well, but what happens if you don't have enough training examples? Or what happens if the statistics of your test data is very different than that of your training data? In those cases, deep learning fails quite miserably. And what we would like to show you is how we can often overcome these problems by replacing external learning with internal learning. And as we will show you, this gives rise to lots of applications, including super resolution from a single image, temporal super resolution from a single video, image dehazing, image segmentation, transparency separation, image retargeting, and more. So let's start. So how can we train a network on a single image? Well, it turns out that there's a lot of redundancy inside a single natural image, which often suffices to give us all the statistical examples we need to solve our problem. The recurrence of information happens both within the original scale of the image as well as across scales. When I say within scale, I mean that if you see a small patch once inside the image, you'll almost surely see it many more times inside the same image. Now here I'm showing you relatively large patches for display purposes, but in practice I'm talking about much smaller patches, 5 pixels by 5 pixels or 7 by 7. And this has been used by us and by many others for lots of applications, including image completion, image denoising like non-Malcolm means and BM3D, visual summarization, and many more. Less commonly used, but also very strong, is the recurrence of patches across scales in a natural image. That is to say, if you scale down the image, then almost any patch in the original image will almost surely be found as is without downscaling the patch in a coarser scale of the image, which means that tiny patterns appear in multiple sizes in the original image. And I'm talking about much smaller patches and much smaller patterns than what you see here. And this has been used by us and by others for lots of applications, including fractal image compression, super resolution from a single image, blind deblurring, blind dehazing, and more. Now, this may look like a contrived image to you, and you may ask, well, does it go beyond images with such clear repetitive structure and such perspective projection? And the answer is yes. If you go to small enough patches, 5 by 5, 7 by 7, this is true for almost any patch in almost any natural image. For example, here is an image where you don't see perspectivity and no clear repetitions, but if you look at the patches along this edge, they recur many more times along the same edge. And similarly, across scales, an edge patch appears as is without scaling down the patch. Or similarly, corner patches. Okay, so repetitive structure, edges, corners. What happens if you go to an unstructured texture like this? Does it still hold? Well, let's zoom in and see. And you can see that locally, we still have the same statistical patterns. It turns out that this fractal-like property is a very strong property of natural image, even if you don't see the repetitive patterns, even if you don't see perspective projection. And we showed this empirically in our 2009 paper. We checked it for hundreds of natural images, tens of millions of small 5 by 5 patches, indoor images, outdoor, man-made, natural, and it turns out that this is true for almost any small patch in almost any natural image. So as I said, this gave rise to lots of applications over the past 2 decades in computer vision. And the nice thing about these approaches is they're totally unsupervised. They don't require any additional examples other than the test image itself. Okay, all the information, all the statistical data is already, all the examples are already found inside the test image. The bad news is that in the past few years, these methods have been completely outperformed by deep learning methods, which is very depressing. So for a while, I was walking with this uneasy feeling that on one hand, we have this very powerful tool, deep learning, which is amazingly powerful, but it's really data hungry. It requires lots and lots of training examples, and we don't really understand what it is implicitly learning. And on the other hand, we have this internal redundancy, which we understand and requires no prior examples, is self-supervised, but doesn't perform as well as deep learning. And for a long time, I was asking myself, is there a way to combine the power of these two very complementary approaches? And luckily, 3 years ago, Assaf Shocher, who was then a starting PhD student and now is nearing graduation, came up with a brilliant idea of doing deep internal learning. That is to say, let's train an image-specific CNN at test time on examples extracted directly from the test image alone. And as you'll see shortly, these things can often be done quite efficiently. And so we applied it to a wide variety of applications, but the first thing we started with was super resolution. And at this point, I'll hand the stick over to Assaf.
Thanks, Michal. So a brief reminder about super resolution. So when given this low resolution image, we want to create a high resolution version of it. And we know that each pixel in the low resolution image is a result of a convolution with some kernel and then subsampling. And of course, this is an ill-posed problem, so some kind of prior is needed in order to solve it. And the case is even much harder if we don't know the exact degradation process. Now, the leading methods for super resolution currently are deep learning-based methods, or as we refer to them, externally trained CNNs. So these work as you probably would expect them to work. So you have this large training set containing pairs of images, low resolution and high resolution, and you train a big network for hours or days or whatever needed, when the low resolution images are the inputs and the high resolution counterparts are the labels. And then once trained, you can apply this to a never seen before image to get the super resolution result. And impressively, this gets results that are much better than any of the classical or patch-based previous methods. But there is one big problem. And the problem is that they work well only under ideal conditions. And the bad news is that real images are not ideal. So let me clarify what I mean by non-ideal. So remember that the low resolution images in the dataset were downscaled from the high resolution images using a predetermined degradation method, usually by cubic downscaling with anti-aliasing. And therefore, the networks that train this way, they're only applicable for images that were downscaled exactly in this same way. So there's nothing you can do with them to real images or anything that was downscaled differently. The second thing is that they cannot handle artifacts, be it JPEG compression or just noise. So externally trained networks, they tend to amplify these artifacts. And recently people try to do blind super resolution. And the first thing you would try to do, the naive way, is to do it supervisedly, trying to train a big network to be agnostic to the kernel by training for many random kernels. Now, for various reasons, this thing doesn't work, this can't work. And we chose a different approach. So we thought, why do it externally? Why not training a network just on this one single image and do it by internal learning? And this is our work called zero-shot super resolution. This is also together with Nadav Cohen. And in this work, we said, okay, so we're going to take this one input image and we'll do the counterintuitive thing, and we're first going to downscale it. And now we're going to feed it to a network that is a small network, which is image specific. It trains only on this one single image to produce back again the original input image. And to make sure it does, we use this autoencoder-like style loss, and we'll train it for a while. And then we can apply the train network to the original image again to get the super resolution. Now, the reason this thing works is that this is a fully convolutional network. So it trains on patches. So basically, it learns how to super resolve patches from the low resolution image. Now, because we know that patches recur across different scales of the image, then we can meet the same patches, the same patch distribution also in the original image. So if we know how to super resolve patches from the low resolution image, we also know how to super resolve patches from the original image. And to make it generalize even better across the scales, we use augmentations that are made just from this one single image. So we do flips and rotation and scaling to the image we train on. So what about downscaling? So in order to know the correct method to downscale the image, at the time we first used this work by Tamar Michaeli and by Michal Irani, and to estimate the kernel just internally from the input image itself. And later Michal will show you a recent work of ours, which we used to estimate the kernel using an internal GAN. So how can we do this at test time? How can this be trained fast enough? So we need to distinguish between internal training and external training. So the entropy of patches inside a single image is actually much smaller than the entropy of a large data set. This was shown in our lab long ago. And this means we can use a much lighter network, which in turn means we can do much faster training. Actually, it can be just 9 seconds for both the train and test time. So having this network that learns on the fly helps us to adapt to anything. So we can do it to any type of data, like not only natural images, and to any type of degradation. And also we can decide on the fly whatever scale factor or aspect ratio we're interested in. And so this is what we call super resolution in the wild. Okay, so let's see some results. So this is an image that was downscaled in a non-ideal and unknown way. And this is just a simple interpolation. And now I'm going to show you super resolution results of a method called EDSR, which is like almost state-of-the-art, externally trained network. And you can see that there is almost no difference. If we flicker between those, you can hardly spot any difference. And the reason is that these externally trained methods, they're only good for ideally downscaled images. And once taken out of their comfort zone, they really can't handle this. And in the contrary, here is the ZSSR results, our internally trained network. And you can see that this is much sharper and much better details. You can see some details here that go beyond the Nyquist frequency. That means that in the original input image, they're actually smaller than one single pixel. Here's another one. So this is checkpoint Charlie, and this input image suffers from severe artifacts. It has both JPEG artifacts, some noise, and unknown downscaling. And again, this is the interpolation. And if we flicker between the interpolation and the externally trained state-of-the-art EDSR, then you can hardly spot any differences. But if we go to the internally trained ZSSR, you can see a much sharper image. If we zoom in a bit and flicker between them, then you can actually see much big differences. For example, the gap between this guy's legs over here. And the reason is that ZSSR adapts on the fly to the image-specific degradation. This is a JPEG compressed image, and in this case, what the externally trained methods do, they really love high frequencies. So they see high frequencies, they just amplify them, and that's why we get even worse artifacts. ZSSR does a much cleaner job, and the reason it does so is that the signal recurs across different scales. So the patches of the signal recur across different scales of the image, while the noise doesn't. The noise is not correlated, so it's harder to reconstruct it. As for the numbers, so for the ideal case, ZSSR does reasonably well. It's ballpark from state-of-the-art networks, but the real advantage is for the non-ideal images, where we get really a huge gap, both visually and numerically, 1 to 2 dB.
So, fundamental to any super resolution method is the ability to use the correct downscaling kernel, the kernel that was used to generate this low resolution image. But we don't know what this kernel is, right? And it changes from image to image. It's not only camera specific or photographer specific, It also depends on the way I move my hand when I took this image. And we saw already that simple bicubic downscaling will not help, neither external learning nor internal learning. We have to use the correct downscaling kernel. But how are we going to know what it is when we don't know the high resolution image? This is what we want to recover, nor do we know the kernel relating the two. And we need this kernel in order to downscale the image, in order to generate training examples to train the network, whether internal or external. Well, it turns out that in our paper in 2013, Tamar, Michaeli, and I showed that the correct downscaling kernel can be recovered directly from the low resolution input image itself. In fact, we showed that the correct super resolution kernel is also the kernel such that when you downscale the low resolution image with it, will maximize the similarity of patches across scales in this image. And you can find the analytic proof for this claim in our 2013 paper. Back then, we posed it as an optimization problem and solved it as an optimization problem. But more recently, we found a way of computing the image-specific kernel using deep internal learning. We call it kernel GAN. We estimate the kernel using an internal GAN. This was a recent NeurIPS oral half a year ago by Steffi Belkligler, and of course also Assaf. And the idea is the following. We have a single low-resolution input image. That's all we have. We've never seen anything before. And we want to estimate its kernel. We're going to use an internal GAN for that. The generator of the GAN is going to learn how to downscale correctly the image. What is good downscaling? Good downscaling is the one that maximizes the similarity of patches across scales of the low resolution input image. How are we going to guarantee that this is what the generator does? Well, we're going to feed crops from this image into a discriminator. Sometimes gets crops from this image and sometimes gets crops from the original input image and has to tell them apart. It will generate a map which says for each pixel whether the patch surrounding it came from the original patch distribution the original distribution of patches in the input image, or from the fake generated distribution of patches in the downscaled image. And so the generator will get better and better in trying to fool the discriminator to believe that these are the low resolution, the input patches in the original image. It will try to make it as similar as possible to them. Whereas the discriminator will try to get better and better at distinguishing these. And when the GAN converges, the generator will converge to the correct downscaling kernel. Now, note that the generator cannot be just any deep network. A regular deep network is nonlinear. It can generate a garble of patches. It can even collapse to a single patch in the low resolution input image. The discriminator will be happy. It says, yeah, this patch came from the input image. The generator will be happy because it fooled the discriminator, but this is obviously not what we want. What we want is for the generator to produce something of this form, convolution with a kernel and subsampling. And if you look carefully, you'll note that this is a linear operation. In fact, it can be realized with a single strided convolution layer with a single unknown kernel. So that's what we try to do. We try to replace our generator with a single strided convolution layer that has only one unknown kernel. That worked horribly. If these were the ground truth kernel, this is what our generator produced. And no matter what we did, we couldn't make it to work well. And we couldn't understand what was going wrong until we realized that the reason this happens is because if you think about it, deep networks work well because they don't have any bad local minima. They're over-parameterized. They have infinitely many possible solutions, but all of them are equally good. So no matter how you initialize the weights of your network, it will always converge to a good local minimum. But this is not the case here. Here, we have only a single good minimum, the correct downscaling kernel K, and no other minimum is good, okay? Now, if we randomly initialize our generator, it will unlikely converge to the correct minimum. It will get stuck in some bad local minimum. And remember, the error surface of our generator is highly non-convex. It doesn't only have to solve this linear operation, it also has to fool the discriminator. It has to satisfy the GAN loss. And so it's highly non-convex. So this will never work, okay? What does work, however, is replacing the generator with a deep linear network. What's that? That's a deep network that has no ReLUs and no nonlinearities whatsoever. And if you multiply the weights from all the layers, gives you the single correct kernel K. So have we gained anything? Isn't this exactly the same? No, it's not the same. We've gained a lot. Why? Because in a single strided convolution layer, we had a single good minimum, the correct downscaling kernel K. That was the only solution for the network, the only possible weight combination. Here, on the other hand, we have infinitely many decomposition of the single kernel into many possible weights in our layers. For example, if this is a good decomposition of the network, then so is this one. We can multiply the weights of one layer by a matrix A and the weights of the next layer by the inverse of A, and still we'll compose all of them to the single correct kernel K. And this is true for any invertible matrix A, and you can put it between any two layers. So you have infinitely many decompositions of the network, or in other words, we have infinitely many good local minima. We have infinitely many possible weight combinations that will give us the same correct global kernel K. And now, when we initialize our network randomly, it converges to a good local minimum. And so, if here are the ground truth kernels, and these were the result of the single-strided layered generator, these are the results when we replace our generator with a deep linear network. And you can see that this solved the problem. And as far as we know, this is the first practical use of deep linear network. So far, deep linear networks were only used by theoreticians for analyzing and proving things about deep networks. And here we show that this is actually practical for solving linear regression problems under nonlinear priors. So let's look at some results and comparisons to other blind super resolution methods, external ones. So here is a real old low resolution image of Ted Kennedy. We have no idea how it was generated. What you see here are the results of the two winners of the Blind Super Resolution Challenge at Empire 2018. It was called Super Resolution in the Wild. They did well on the wild dataset of that challenge, but once you take them out of their comfort zone and apply them to real images, they perform quite poorly. In contrast, what you see here on the right column is the result of our internal zero-shot super resolution, where the kernel, the downscaling kernel we supply it, was computed using kernel GAN. And if you look carefully, you'll see the two pupils of John Kennedy. It turns out that he was cross-eyed, whereas you cannot see them in these externally trained methods. And true, they look smoother because they were trained to produce smooth-looking images, but they don't produce the correct results. What you see in the third column here is our internally trained ZSSR, but with our older 2013 non-deep way of computing the kernel. And you can see that it doesn't do as well as kernel GAN, but it still does better than those externally trained methods. And here's another example. And once again, on the right, you can see the best result, which is that of ZSSR using the kernel computed by, the image-specific kernel computed by kernel GAN. And we, of course, did a lot of empirical evaluations, which you can find in the paper. Up to the time of the submission of our paper, the methods that were available then, we did half to 1 dB better than any of those methods, whether super resolution methods, where they're blind or non-blind. And of course, there's been a surge of blind super resolution methods since then. But I'm happy to say that in the recent NTAR challenge in CVPR 2 months ago, NTAR 2020, the winner of the blind super resolution method used our own kernel GAN to estimate the image-specific kernel for each and every image.
So up until now, we showed you deep internal learning mainly for super resolution using an image-specific network, which is good because it's unsupervised and you can do it just on the test image itself, and you can adapt it on the fly to any type of degradation and eventually get state-of-the-art results for real-world images. But we were wondering, can we use this logic maybe for other tasks? What about image segmentation to the foreground and background? What about dehazing? Or for example, when you take an image, when you take a picture through a window and want to separate it to reflection and transmission. So one key observation that made it possible is that many seemingly unrelated computer vision tasks can be put under a single umbrella of decomposing an image to 2 separate layers. So for example, look at the zebra image over there. We can express the zebra image using saying that it's the segmentation mask multiplied by a zebra pattern plus the anti-mask multiplied by the background. Similarly, the transparency separation, the mixed image, is a linear combination of the reflection and transmission. And also for dehazing, the mask now is the transmission map multiplied by the clean image, or the anti-transmission map multiplied by a thing called the air light. In all of these cases, the mixed image is actually a linear combination of 2 layers using a spatial mask. So this brought us to our paper called Double Dip, together also with Yossi Gandelsman. And DEEP actually stands for Deep Image Prior. So we were really inspired by this work by Ulyanov, Andrea that was here before, and Victor Lempitsky. And for those who missed this talk, so their idea was quite simple and nice. So given this input image, we're going to train a network, fully convolutional, only on this image alone, and we're going to train it to overfit to this single image. And of course, this is a very easy task to overfit to one image, and very fast you can get this reconstruction result. But they also noticed that if this input image happens to be noisy, then you can stop at some intermediate iteration and get what seems to be very close to the clean image. And the way we formalize the reason for it is as follows. So the entropy of patches in the clean image is much lower than the entropy of the patches of the noisy image. And if we look at patch recurrence, so we know we have high patch recurrence inside a single natural image. So we check out these two patches, but if we look at these two exact patches in the noisy image, they're not that similar anymore. So the reason Deep Image Prior is able to clean this noise is that a narrower distribution of patches is much easier to create. It's the natural solution for it, and all the noise and high frequencies, they come later in the training. So we can also check this logic on mixture of images. So if we take these two patterns, for example, and we mix them, we get this mixed pattern, and mathematically we know that the entropy of patches of the mixed image has to be greater than both entropies of patches of each of these X and Y images. And we actually tried to train Deep Image Prior for each one of these three images, and we always got the same result, that the training for the mixture always takes more time than training for each of its sub-parts. So, armed with all these observations, we came up with the architecture of double deep. So here's how it works. Given this mixture of images, some kind of mixed image, we're going to train now two deeps. And we're simply going to require that the sum of the results is going to be as close as possible to this mixed image. And again, overfitting a single image is very easy, but here is where the magic happens. So it turns out that at each side of the double deep, we're now going to get a separate layer of the image. And the reason this happens is that this is the most natural solution for these deeps, because the distribution of patches for every layer is narrower than any mixture of layers. Okay, so we help it a little bit in the beginning with a thing called exclusion loss, which basically encourages no correlation between the results of between the outputs. And we actually don't have to just use the summation of these outputs. We can use a spatial varying mask. And this mask is also learned. And the thing is that the regularization over the learning of this mask is what determines the type of task that we are performing. So, for example, if we want to do now image segmentation, so now we're going to encourage the mask to be binary. And once again, we're able to reconstruct the image, but now what's going to happen is that the learn mask is going to learn to be the segmentation mask, while the foreground and background are going to be splitted to both sides of the double deep. And this is because the foreground and the background have different distributions of patches. So this is the easiest, most natural solution for double deep to converge to. And this can be used to many tasks. So first, for the segmentation, we can get really nice results. Now, this isn't semantic segmentation, and I don't think it's state-of-the-art results, but it certainly does impressive things if you think about it, that it's never seen any examples. So, for example, clustering these two ladies together, or these three soldiers, or doing some non-trivial boundaries and textures, like in this example. For dehazing, we actually got what was state-of-the-art results at the time, really good, impressive results. And as a bonus, we also got the transmission map, because this is actually the mask that we learned, and you can actually infer the depth from this transmission map. In this video, This video was actually taken through a window, and we were able to split it to the reflection and transmission. And we, in layer 2 over there, you can see that we were able to retrieve this Buddha statue, which is hardly noticeable in the input video. Going a bit to the malicious side, so watermarks for security, for images security in the internet are actually another type of layers. So we can decompose a watermarked image to the watermark and the image itself. Now, all of these applications were done without any prior examples and no pre-training, and was totally unsupervised, just from this one single image itself. Okay, so now we know that there is a unique role for the distribution of patches inside a single image. And we're thinking what else we can do with this distribution. And one thing we really wanted to do is to use images to create another version of them that shares something in common. We call this the DNA of an image. So in this example, this bigger image contains the same elements as in the lower image. So the windows are at the same size, but we just have more of them. And this is because it shares the same patch distribution, only a different shape. So this is what we were after in our work called InGAN, internal GAN, and this is together with Shai Bagon and Philip Isola. And what we were aiming for is to feed a generator network with an input image and a transformation. And this is a special transformation that changes the image. So in this example, it stretches it in the horizontal dimension, but we want to preserve the patch distribution. In this example, we create this visual summary. So it has less windows and everything and every element is the same, but we just have less of all the elements. So it's kind of a thumbnail for the larger input image. So to make sure that this is what it does, we need a discriminator. And this is a patch discriminator. It's fully convolutional, and rather than just producing a scalar, it produces this map. And this map, in this map, every pixel says to what extent the discriminator believes that the matching patch in the receptive field actually came from the original image. So the generator's job is to fool the discriminator to believe that the patches it sees actually came from the original input image. Now, internal overfitting is a thing. So what if we generate an image only containing grass? The discriminator was happy about this because all of these are valid patches. So to make sure this doesn't happen, we're going to use this cycle consistency, and we're going to feed the image, the output image, again to the generator in order to reconstruct the original input image. Now, this is the same generator with shared weights. The only difference is the type of transformation we feed to it. So now we're going to feed the inverse of the original transformation we used. So this is an encoder-encoder architecture as opposed to encoder-decoder because we're using the same generator to do the same task back again. Okay, so let's see some results. So here you can see in this fruit stand how it can be stretched drastically, but still all the fruits maintain their original size. So if needed, fruits are added and removed and boxes are added and removed, but all of them maintain their original path distribution. And it doesn't have to be just resizing. So the transformation can be any invertible transformation. So it can also be general homography. And even though the global shape is now changing, so the local elements inside the image maintain their original shape and size. Here you can see how more windows are added and removed from the building. And here you can see our poles are added, or our penguins are not getting fatter, but only new ones are getting born. And remember that no one's perfect. So we don't know nothing about humans and how many heads they should have. So this is the result InGAN produces, because this is simply from the patch distribution. So this is kind of a failure example, but an interesting one.
All right. So far we saw how we can apply deep internal learning to images. More recently, we tried extending this notion of deep internal learning also to video. Can we train a deep network at test time on the test video alone? And the first task we tried it on is for zero-shot temporal super resolution. And this paper was presented at ECCV this week with Liad Polak, Eyal Naor, George Pisha, Shai Bagon, and myself. And the idea in temporal super resolution, just to remind you, in spatial super resolution, we have a low pixel density and we want to increase the pixel density inside the image. In temporal super resolution, we have a low frame rate video and we want to increase the frame rate of the video. For example, take a 25 frame per second video and generate a 200 frame per second video from it. But we don't want to just temporally interpolate the video. Temporal interpolation does not recover any new information. In temporal super resolution, we want to be able to recover dynamic events that occur faster than frame rate. We want to go beyond. The temporal Nyquist limit of the video camera. We want to be able to undo motion aliasing and motion blur. These cannot be undone with temporal interpolation. Here is an example of temporal aliasing. What you see here is a fan rotating faster and faster clockwise. At some point, it appears to be rotating counterclockwise, and this is simply because we're not sampling it fast enough in time. This is only a 25 frame per second camera, so we cannot capture this dynamic event. The other thing that happens is motion blur. From the moment the shutter of the camera opens until it closes, the fan moves very fast, inducing motion blur. Now note that these two effects cannot be undone by temporal interpolation, no matter how sophisticated it is. Temporal interpolation cannot undo motion aliasing and motion blur. In contrast, in temporal super resolution, our goal is, while we increase the temporal frequency, also to remove motion aliasing and motion blur. And our idea is very similar to the zero-shot spatial super resolution that Assaf showed you before, only here we extend it to the space-time volume. And the sophistication here comes in the type of internal augmentations we use to do in the space-time volume to generate these internal examples. So you can find many augmentations in our paper, but let me display here two very useful ones. One very useful augmentation is blurring and subsampling the video in time. Okay, we generate coarser and coarser temporal scales. The video frames remain the same size, but the videos get shrunk in time, fewer and fewer frames. So if this was the original video of a rotating fan, then in a coarser temporal scale, this is what we will see, a blurrier fan moving faster. And in a yet coarser temporal scale, this is what we will get. We will already see motion aliasing with very severe blur. In other words, when we generate coarser temporal scales, we actually synthesize the same dynamic event, but with higher speed, more motion blur, and more motion aliasing. We will now train a video-specific CNN on these pairs of examples, of video examples, to learn how to undo the motion blur and motion aliasing of this particular dynamic scene. And once trained, we can apply it to the original input video to generate the temporally super resolved output. Another very useful augmentation is based on our totally new observation. And this is that patches in the video not only recur across space-time video scales, they also recur across video dimensions. What do I mean by that? Well, here's the space-time volume of the video. If we just look at the spatial slices of this volume, these are the video frames we're all used to seeing. But if we now take the space-time volume and rotate it so that one of the spatial axes becomes the new temporal axis, and now slice it, okay, then we see those space-time slices. Note that they look very similar to the frames up there. The space-time slices look very similar to the cheetah that you see here up in the frames, but they contain aliasing in time, which we don't have in the original video frames. So the video frames can actually serve as high-resolution examples as to how to undo the temporal aliasing in the space-time slices. And you can find many more details in our paper, but let me show you some results. So what I'll show you, the results are temporal super resolution by a factor of 8, taking a 25 frame per second video and turning it into a 200 frame per second video. So here is the example we saw before. At the top left is the original input video. At the bottom left is our result. And you can see in the other places our competitors, NVIDIA Slow-Mo, Dane, and Flawless. And you can see that they cannot handle the motion blur and motion aliasing, whereas our fan now in the super result output rotates clockwise all the time and much less motion blur. Here's another example, a rotating disc. At the top left is the input, played in slow motion. At the bottom left is our output. It's not perfect, but it's much better than any of the competitors, NVIDIA Slow-Mo, Dane, or Flawless, that cannot handle neither the motion blur nor the motion aliasing. Of course, the motion does not have to be repetitive. Here you can see a single beach flip, and here are the results. Again, upper left is the input, bottom left is our result, bottom right is the ground truth. And you can see that we remove the blur much better than many of the competitors. By the way, Flawless does extremely well. And of course, the motion doesn't have to be rotational. It can be a chaotic motion. Here are falling diamonds. Again, bottom left is our result. Bottom right is the ground truth. And you can see that we do better than most of the competitors. You can find many more video examples in our project website. You can see also examples of highly non-rigid scenes, flickering fire, splashing water, and many other complex scenes. To summarize, I hope we've convinced you that there is a lot of redundancy inside a single natural image or a single natural video, and that we can apply this in order to do deep internal learning. It combines the power of deep learning with internal image-specific priors. It allows to train a network in a totally unsupervised way. It needs nothing but the input signal. It adapts to the unknown imaging conditions and degradation of the specific input test image or video. It gives us state-of-the-art super resolution results on real non-ideal images, but it can also do image dehazing, segmentation, transparency, separation, retargeting, and more. What's next? Can we apply this idea of internal learning to high-level vision tasks? Can we apply it to more sophisticated video analysis tasks other than temporal super resolution? What about combining the power of internal and external learning? Can we get the best of both worlds? And Alyosha will actually talk about this in his talk in third session. Can we apply it to other type of signals, maybe audio, maybe fMRI? And Assaf and I would like to thank all the people who worked with us on this variety of papers that we presented, including Shai Bagon, Yossi Gandelsman, Sefi Belkligler, Philip Isola, Liad Polak, Eyal Naor, and George Pisha. So thank you for your attention, and we'll be happy to take questions if you have any.
Great talk. There are a few questions. I'll read some of them. May I know if the size of the input image of the ZSSR network is different at train and test? If they are different, how to implement it?
So they are different, and actually there is no problem with this, since this is a fully convolutional network, and fully convolutional networks can get any size of input. So at test time, naturally, it's a larger input with the ratio of the scale factor.
I didn't hear. The question was about the image or the network itself?
Yeah, the image. And okay, there is another question. Thanks for the great talk. A wide range of applications of super resolution and other tasks that you mentioned require real-time performance. Would deep internal learning be applicable for real-time practical use cases, since training is required for each test data?
So I think this is where the combining the power of internal and external learning should come. Okay, right now we train from scratch a deep network for any new image that comes along. We believe that the right thing to do is actually to combine the power of prior data. There's a lot of data which is common to images, and then there is this image-specific data and image-specific degradation. We haven't found the right way of combining them yet, but I know that people are working on this and there are initial good results, and I believe this will lead to real-time performance of deep internal learning. Do you want to add anything? No.
Okay, another question. When kernel GAN is applied on the same image multiple times, it produces different looking kernels. Some of them are very different from each other. This was observed both on real and synthetically degraded images. How can we solve this problem?
So the reason it happens is that for each time we do it, we retrain a network. So what we observed is that they're not too different from each other. So statistically, this can happen. And perhaps for future work, this should be stabilized by some kind of regularization. But this is one of the aspects of deep internal learning. You retrain rather fast, but you retrain a network for each time you perform the task.
Okay, there is one more question. For ZSSR, is the architecture a multi-scale architecture?
So it's not a multi-scale architecture, but there is a multi-scale procedure that you can make. So basically just training for intermediate scales and then adding the results as augmentations, and this allows better results for the higher scales if you do this for high scales.
Just adding to what Assaf said, we gradually apply the super resolution. If we want to super resolve by a factor of 4, we don't immediately train a network to resolve by a factor of 4. We train a network to resolve by, let's say, 1.5 or 25% at a time, and we gradually increase the resolution, thereby generating more and more training examples for this process. In that sense, it's course defined, not in the image pyramid sense.
Okay, great. I think we need to move on to the next session. So thanks for the great talk. And next up is a short oral session. So we're going to play 3 short orals, one after the other, and then we'll have time for questions and answers. If you have questions, please write them in the Q&A chat, and please indicate to which of the 3 papers you're referring. And we hope the authors of all the 3 papers are here. If not, then we'll present questions only to those who are here. Okay, so in a minute, we'll start the videos.
Hello, everyone. I'm Pang Yingxue from University of Science and Technology of China. It's my honor to stand here and share our study, 2GAN, Learning Versatile Image-to-Image Translation with 2 unpaired images. This work is conducted together with Microsoft Research Asia and the University of Rochester. To achieve unpaired image-to-image translation, existing models need to collect numerous unpaired images from both the source and target domains. However, we often come across cases for which there might not be enough compared data to train the image translator. An extreme case resembles one-shot unsupervised learning, where only 1 image in the source domain and 1 image in the target domain are given but unpaired. There has been many works related to our paper. CycleGAN and DRT both requires 2 sets of images as source domain and target domain. FUNIT requires a large amount of visible training data. OSIT requires a set of images from the target domain. Our problem setting is also different from image style transfer. Not only the style, but the high-level semantic information should also match in our model. Our model is also different from single image generative model, SynGAN. SynGAN is trained to learn the internal patch distribution of a single image. In contrast, our model aims to capture the distribution variations between 2 unpaired images. We propose the 2GAN, which is able to transfer domain distribution of impulse image to the target domain by progressively translating image from cause to file. We'll introduce more details in the following slides. Given translation direction that translates image A to domain B, for example, at scale n, we can impose image IAN to generator GABN to produce translation result IABN. For images with scale smaller than n, we have 2 inputs, 1 current input image and 1 previously translation result. Finally, we can obtain the translated results at a scale 0. In order to better combine 2 scales results, we introduce a scale-aware generator. We first use a convolutional network file to produce the initial translation. Then, we use the attention model to generate a mask, which models long-term and multi-scale dependencies across image regions. Finally, the initial translation results and previous translation results are linearly combined through the generated attention mask to get the final output. At scale n, there are 2 discriminators. We choose WGNGP as adversarial loss. We utilize cycle consistency loss to constrain the model to retain the inherent properties of input after translation. We noticed that relying on the 2 losses mentioned above could easily lead to color and texture misaligned results. Therefore, we introduce the identity loss at each scale and total variation loss. We first conduct general experiments on several translation tasks to verify effectiveness of our algorithm. We demonstrated the effectiveness of our 2GAN on two kinds of image style transfer tasks. The first one is art style transfer, and the second one is photorealistic style transfer. To compare with FU90, we conducted the animal face translation experiments. The painting to image translation task focuses to generate a photorealistic image with more details based on roughly related clip art. For quantitative comparison, we use three metrics. The lower SIFID and the lower PD scores indicate that the style and context of two images are more similar respectively. As for user study, compared with DRT trained on full data, our model also achieves similar votes from subjects. Also, we conduct several ablation studies based on house to zebra task. In this paper, we proposed the 2GAN, a versatile conditional generative model that's trained only on two unpaired images. Our model is designed in a cost-effective manner, in which two pyramids of conditional GANs refine the results progressively, from global structures to local details. Overall, our work represents a further step towards the possibility of unsupervised learning with extremely limited data. Thanks for your attention. Welcome any question.
We present Deep Single Image Manipulation by Yael Winker, Eliyahu Horvitz, Nir Tzabari, and Yedid Choshen. Users often wish to manipulate images. Consider this image, for example. We may wish to change the position of the nose or tilt the eyebrows. Manipulating the pixels of the image directly is typically very hard for humans. One alternative way of manipulating images is by representing them as simpler primitives and manipulating the primitives. One example of a primitive representation is the edge map. Other primitives include semantic or instant segmentation maps of the image. After manipulating the primitives, we then need to map the primitives back to photorealistic images. The mapping can be performed using a deep neural network. Popular methods include Pix2Pix HD. The described image manipulation paradigm suffers from two notable issues. First, training a primitive-to-image network, for example using Pix2Pix HD, typically requires a large training dataset. Although large datasets are available for the most popular image categories, such as faces, cars, or cats, unfortunately, datasets for the long tail of less frequent images are not available. Another issue is that when trained on a large dataset, the mapping network may not map the primitive to a similar image, losing the original identity. In order to overcome the issues we mentioned, we propose a new approach which we name Deep Single Image Manipulation, or DeepSim. Our method learns a mapping network based on just a single pair of primitive and original images. We expand the single image pair into a large paired training dataset. We then train a primitive-to-image mapping network on the expanded dataset. We expand the dataset by performing the same random augmentation on the primitive and original images. One way of doing this is by performing random cropping and horizontal flipping. However, this simple augmentation does not result in sufficient variation. Instead, we propose to perform the augmentation using a random thin plate spline, in short TPS augmentation. The TPS transformation is smooth but highly non-affine, which dramatically broadens the range of manipulations available in the expanded dataset. During training, we randomly sample a TPS transformation and equally warp the primitive and original images. We then optimize a Pix2Pix HD network using the warped primitive as input and warped photo as output. This is done for 16,000 random warps. Let's see some results. This space is represented using the edge primitive. By manipulating the primitive image, we are able to move the nose. Another manipulation of the primitive image tilts the eyebrows. This car is represented using a segmentation primitive. By manipulating the primitive image, we are able to add a third wheel to the car. Another manipulation of the primitive image transfigures the sedan into a sports car. The edge representation allows fine manipulation but has weak generalization properties, for example, the eye of the bird. Segmentation maps generalize well but do not allow fine control. For example, consider the loss of detail in the background. We propose a new representation, which we name the superprimitive. This representation consists of the edge and segmentation maps overlaid together. It combines the strengths of both representations, allowing for fine control and good generalization. Notice the detailed background and sharp eye after rotating the head. We present another example. This image consists of 3 cars. We represent it using the superprimitive. By removing the car on the left and completing the missing edges, we are able to completely remove the leftmost car. By switching the segmentations of the cars and completing the edges at the back, we are able to switch the positions of the rightmost cars. We also presented a novel way of numerically evaluating single image manipulation methods based on video datasets. Our method performs much better than the baseline, resulting in much smoother generated videos. To summarize, we presented DeepSim, a new method for learning image manipulation from a single pair of images. Differently from other methods, our method does not require a large dataset and preserves the original image identity with high fidelity. Please consult our archive manuscript for more details and results. Our code is available on GitHub. Thank you for listening.
In this talk, we'll present structural analogy from a single image pair. We consider the problem of generating structural analogies. Given a source image of balls and a target image of marbles, we wish to generate an image that 1. Follows the spatial distribution or structure of the balls, and 2. Depicts the internal patch statistics of the marbles. The generated marbles look realistic and are of the correct shape, but follow the spatial distribution of the balls. This can also be done in the reverse direction. And in many other examples, such as translating between ducks and orcas, or translating between pumpkin and balloons, as well as translating between plants and a log. Our work is related to style transfer methods and to deep image analogy. Both operate on pairs of images. However, unlike our method, neither method can change the shape of objects in the image. Note how the shape of the building and the shape of the face remains intact. In contrast, our method can change the shape of objects while creating analogous solutions. Given an image A of snow steps and image B of dog footprints, our method generates an image of snow steps that follows the same spatial distribution of dog footprints, while depicting the same features from the source snow steps image. This is also true in the reverse direction. Our key idea is to produce a mapping between the multi-scale patch distribution of A and that of B. At core scales, the spatial alignment of the dog footprints must resemble that of the snow steps. At a finer scale, a patch containing 2 footprints next to each other is mapped to 2 snow steps next to each other. At even finer scale, the upper part of the footprint is mapped to a small snow step, and similarly, the bottom part. Note how the snow steps still remain human-like and not dog-like. That is, our method preserves the internal statistics of the snow steps, while creating an analogous image to that of the dog steps. Our approach consists of an hierarchical structure. Our hierarchy starts at coarsest level 0, and moves to the finest level, n. We begin by unconditionally generating random samples of the same patch distribution of A at this scale. This is done by adding a random noise Zn to A at the previous scale, and passing it through A's generator GA. We utilize a patch discriminator to distinguish between real and fake patches of A at this scale. Given a random, unconditionally generated image AN, we now pass it through B's generator, GB. We first require the conditionally generated image AB, N, to be of the same patch distribution as B at this scale, using a patch discriminator. Next, we enforce a matching between the patches of A at this scale and the patches of B at this scale. We employ a cycle loss by passing the conditionally generated sample AB, N through A's generator GA and requiring the sample AN to be reconstructed. In coarse scales, we use residual training that helps the network generate aligned solutions. But at finer scales, we do not use residual training, which enables us to generate images of finer quality. Note that the direct interaction between scales occurs through the unconditional generation pipeline only, and so an indirect interaction between scales occurs for the conditional generator. A direct interaction between the scales at the conditional pipeline results in the network cheating, producing unaligned solutions. Our method outperforms existing approaches. Please check the paper for additional details. Our work can also be used to translate between images depicting multiple types of objects. Given images A and B, our method can be used to generate many images of A and B unconditionally, and then produce structurally aligned mappings. Our method can also be used to translate black and white sketch to photorealistic images of the same internal statistics as the target input image. We can also generate text of a specific reference style. Our method can also be used for texture transfer, as well as to perform style transfer. Lastly, we used our method to generate photorealistic videos that are analogous to a source video, given only a single image in the target. Thank you. For many more examples, please visit our project webpage.
Okay, we have time for a few questions. As I said before, if you have questions, please write them in the Q&A chat. We seem to be missing the authors of the first paper, Twigan. So if you're here, please let us know. Please write in the chat so that we can make you a panelist. Okay, we seem to not have any questions for now. I have a question for the second paper, the Deep Sim paper. It seems like when you remove an object, you mentioned that you have to manually fill in the edges, right, in the background. When you remove the car, you have to draw. So this seems a bit, I mean, it requires some skill from users. Is there any way to do it without it? Imaging painting works do that.
Okay, yeah, great question. So it depends. So if the change that you want to do is a very large change, so you might need to manually paint the hole that was created. But if you want to make a smaller change, that you wouldn't have to do it. But we actually like the motivation that the motivation for doing that, like why it is might be okay to manually fill the holes, is that it would be easier to do it in primitive domains such as edges or segmentation rather than do it on the actual image. But indeed, it's like we are aware that it is a yeah.
Tomer, can I ask a question?
Yeah, sure.
I actually have a question, one for the second and one for the third talk. Maybe I'll ask first for the third talk. I think it's Sagi, right? Sagi, when you showed at the end this video of the bird flock based on a video of a balloon, it seemed like the birds were actually going, what do you call this, flattering their wings, even though it was from a single image. I didn't have time to look at it, but does their motion make any sense, or is this just random locations of birds and every time they move it's something else?
Right, so I mean, the motion you get is only the motion you have from the source video. So you wouldn't,
only the global
you only
motion.
have a target image. So we, you know, we couldn't. So in that sense, you only have that.
Yeah. And Yael, I have a question for you too. When you augment your images, you generate it with a spline distortion. My question is, it may be a very naive question, but what if I were to do something, the following naive thing? I want to move the eyebrows like this. If you move the eyebrows like this on your sketch, and now fit the best possible spline to this distortion, and now apply this spline transformation to the image. Wouldn't you get a good looking image?
Okay, so yeah, and actually we have, like, there are algorithms that do that with morphing. They have their target, and by optimization, you can get the best result you can with spline methods. However, these methods are limited. For example, if you would like to erase the eyebrows, or like just like add another eyebrow. So with only spline optimization or like morphing optimization, you wouldn't be able to do that. So this is the first difference. And in addition, I would guess that if you would like to flip the eyebrows, it might, using only morphing, it might also stretch your eyes in an like not a logical way. And this is what makes our method more generalized and better than only morphing.
Makes a lot of sense. Thank you.
Thank you.
I have a question for the third paper, Sagi. I saw that in the pumpkins to balloons example, you had two balloons, one above the other, form the shape of one pumpkin. But in the other direction, you had one pumpkin squeezed, right?
Yes.
To become like a balloon. So it seems like you need to make some user decision what's considered texture and what's considered structure, right?
Yeah, so I think the interesting thing there is that because during training the image did not contain a large enough balloon of the size of the pumpkin, so I decided the most natural thing to do to create the alignment is to actually create two balloons. But on the other direction, it did have sort of a pumpkin in the size of the balloon. So that was the natural way to align the two. But it is indeed something you have to look at and say what's more natural. Sort of baseline methods such as deep image painting, that what they do is they fix the size exactly, so they do not change the size, the shape. Sorry. So what happens is that sometimes those the shape is unnatural to the image created. Yeah.
Okay, I think we need to end this session. So thanks everyone. We're going to have a break. I'll soon put on
What time are we reconvening? I don't have the plan in front of me.
what?
So we will be back, yeah, in 12 minutes.
In 12 minutes. Okay, that's exactly the right time to go to the bathroom, drink a glass of water, and come back. So see you all in 12 minutes. Thanks.
So, welcome back everyone. So this is our second session, and we're going to have a short oral session and then a keynote talk, and afterwards another oral session. So we're going to start by our first short oral session, and this will be on videos.
In this talk, we'll present hierarchical patch. In this talk, we'll present hierarchical patch GAN, generating diverse videos from a single sample. We consider the task of generating diverse and realistic videos given only a single video sample at training time. Our training video and generated videos each consist of 13 frames. On the left are our training videos, and on the right are generated video samples. Recently, approaches to generate diverse images given only a single input image at training time were proposed. We consider SynGAN and a recently proposed extension called ConSynGAN. To generate videos, we use a natural extension of these techniques by replacing all 2D convolutions with 3D ones. As can be seen, Unlike our method, both SynGAN and ConSynGAN are prone to mod collapse and generate videos of inferior quality. We now briefly describe our approach. We first describe a patch formulation of a variational autoencoder that operates on a single sample only. The input to the patch VE is a single video sample, X0. This video is then passed through a fully convolutional encoder E. This results in a spatio-temporal feature map Z', whose spatio-temporal dimension is T times H times W, which we denote as K, each having C channels. As the encoder E is fully convolutional, each of its K features is associated with an input patch of the training input video. N is of dimension C. We then regard each of the K features as an encoding of a separate training patch and apply a VE-KL loss on these encodings. The second part of the patch VE consists of a fully convolutional decoder G0. G0 attempts to reconstruct the input video, and in particular, all of its patches, given the feature map Z'. We now describe our full approach, which consists of a hierarchical structure. Our hierarchy starts at the coarsest level 0, where the training video is of the lowest resolution and frame rate, and move up to level N, where the training video is of the highest resolution and frame rate. We begin at level 0, where a formulation of the patch VE is trained as described earlier. At this level, we use X0, which is a downsampled version of the input video, and is of low frame rate and spatial resolution. Moving to level 1, we freeze G0, learned at level 0, and train an upsampling fully convolutional generator G1 that takes as input the low resolution output of G0 and upsamples it to a higher resolution. We keep training the encoder E using a KL loss and use a reconstruction loss between the output of G1 and the higher resolution version of the input video, X1. We continue this way for M levels, reaching a higher and higher resolution of output videos using our patch VE formulation. After training M levels of the hierarchy using our patch VE formulation, we move to use patch GAN formulation. We apply a similar reconstruction loss to that of the VE formulation. In addition, given a random noise Zm, we use adversarial training to generate novel samples at this scale. Similarly to previous works, we use a patch discriminator D to discriminate between real and fake patches of the video. We continue this way, adding more and more upsampling patch GAN blocks until reaching the final level N. We now demonstrate the effect of using a different number of patch VE levels compared to patch GAN levels. Consider the above training video for their balloons. Using 1 level of patch VE and 8 levels of patch GAN results in mod collapse. On the other end of the scale, using 8 levels of patch VE and only 1 patch GAN level results in significant diversity, but very low quality. Using 3 levels of patch VE and 6 levels of patch GAN results in the right balance with both good quality and good diversity. This can also be demonstrated numerically. Increasing the number of patch VE levels and thus decreasing the number of GAN levels results in improved quality but inferior diversity. Using 2 to 6 patch VE levels out of the total 9 results in both improved quality and improved diversity compared to baseline methods. Thank you. For many more results, please visit our project webpage.
Hello everyone and welcome to our ECCV 2020 workshop talk. My name is Andrea and I would like to briefly present to you our paper, Interactive Video Stylization Using Future Patch-Based Training, which was done as a collaboration between C2 in Prague and SMAP. Our motivation was to help artists in the tedious task of creating hand-painted animations. Last year, we presented a paper on stylizing videos by example. From the given sequence, in this case an Alaskan guy in front of the green screen, we select one frame and let the artist paint over it to produce an exemplar from which the hand-drawn style will be propagated to the rest of the sequence, while preserving high-frequency details and maintaining temporal coherence. While this approach is able to deliver state-of-the-art results, there are drawbacks which make it difficult to use in a real production environment where interactive feedback is inevitable. It's computationally extremely expensive. For longer sequences, it may take hours. It's sequential, meaning to stylize the current frame, the previous frames needs to be processed first. And last but not least, in the case when there are multiple stylized keyframes available, an entire video has to be processed from the first keyframe and from the second keyframe individually. Then an explicit blending operation needs to be performed. Our aim is to preserve the high visual quality of the previous approach. However, at the same time, we'd like to achieve early-time inference, allow for random access to the individual frames, and avoid any explicit magic of sequences stylized using different keyframes. In fact, we would like everything to be as implicit as possible. To approach this challenging task, we draw inspiration from the recent success of image translation networks, in particular FaceTile GAN by Fujik and his colleagues. This approach is capable of delivering high-quality stylized results in real time, but it requires a huge dataset for training. When we apply FaceTile GAN directly on our task, meaning we train the image translation network on a single training pair, the network, of course, strongly overfits to the single training sample, and the results are of poor quality. When exploring the field of deep internal learning, we got inspired by recent published work of Zhou and colleagues, and derived a patch-based training strategy to simulate large dataset needed by FaceTile GAN. From the input image, we randomly sample small batches. We run the patches through the network. We sample the patches from the same corresponding locations from the output image, and we compute the loss between these patches and we propagate the error. During the inference, since we aim for interactive inference speed, we cannot do this on batches. But thanks to the fact that our network is fully convolutional, it only has convolution layers, we can take entire input image and pass it through the network. Moreover, since we do not have any data dependency, we can stylize an entire video in parallel or have multiple images in a single batch. But it was not working just yet. We needed to solve two more issues. First, we needed to tune the hyperparameters, but we didn't have any ground-truth data to validate our network on. We just had one hand-painted style exemplar used to train the network. And second, we needed to enforce temporal coherence so that the resulting video does not flicker in time. To do that, we use a motion-compensated bilateral filter, and we propose a new auxiliary Gaussian mixture layer. Unfortunately, we do not have time to talk about this now, so please refer to our original paper for more details. And once these two issues have been solved, we are able to generate stylized videos of high video quality and temporal coherence. And now, I'd like to quickly show you some more results. We compare each sequence with the approach of Yamirishka and his colleagues to ensure that we provide comparable visual quality and temporal coherence, while we offer fast inference, random access to the individual frames, and interactive experience. Since our approach is really fast in terms of both the training speed and the inference speed, it allows us to come up with various interactive scenarios, which are very engaging for artists. Here, my colleague pre-recorded herself. She printed 2 keyframes on a stencil, and now, while she is painting, the training and inference runs, and a pre-recorded video sequence reflects the newly painted changes on the fly. And now, she just switched to the second, side view keyframe. Note that our approach handles multiple keyframes implicitly. In this setup, a live feed from the video camera is being stylized while my colleague is digitally painting over one captured keyframe in Photoshop. So, if you are interested and you want to learn more, please check out the project page for source code, more videos, and other material. Thank you very much for your attention.
We present an internal learning approach to video imprinting. Video imprinting is the problem of synthesizing plausible visual content within a specified region. It has many practical applications, for example, to remove unwanted objects in the video. Traditional video imprinting methods rely on patch-based and flow-based optimization, which can suffer from distortion. More recently, learning-based methods have shown promising imprinting results thanks to the learned image pairs from a large external image video corpus. However, video data is more complex compared to image data, making it challenging to train a single model on an external dataset to learn effective priors for general videos. In this work, we propose the first internal learning framework for video imprinting. Recent works in internal learning have shown possibility of capturing image priors from the input image alone, which lead to many interesting applications. Different from this work, we study internal learning in videos under the problem of video imprinting. Our work is inspired by deep image prior. DIP uses a simple UNet architecture to map a uniformly sampled noise map to natural image by only minimizing L2 reconstruction loss inside the known region. The striking result of DIP shows that knowledge of natural images can be encoded through a CNN architecture. We start our exploration by directly extending DIP to video while only optimizing one model. We fix the noise map for each frame and map the noise to the middle frames, using the same reconstruction loss on the known image regions. Without any loss constraining the unknown region, we get imprinted regions with high saturation contents. We further involve spatial temporal convolutions into the network by replacing the 2D CNN with 3D CNN. The imprinted regions are better constrained, but still lack of temporal consistency. Finally, we follow the trend of temporal coherent video generation by jointly predicting both frames and optical flows in two opposite directions. We apply L2 reconstruction loss and perceptual loss to constrain the known regions. We then propose the consistency loss by warping the generated frame via the generated flow to constrain the unknown regions in the neighboring frames. Note that to explore the extreme potential of the network, we intentionally restrict our final model only using 2D CNN. Our results shows that it is possible to internally train a single frame-wise generative CNN to produce good video imprinting results that are spatially and temporally coherent. With the consistency loss, our final model can recover the occluded bench. Without consistency loss, the two baselines generate random stones, which is not consistent with the nearby content. To better understand how the model works, we visualize the encoded feature similarity between a reference patch and all the patches in other frames. A higher opacity patch indicates a higher feature similarity. We can see that the most similar patches identified by our alert feature are located on the exact same object across a long range of frames, which is important in ensuring long-term temporal consistency. On the contrary, the feature of a VGG model trained on large image datasets only captures general visual similarity and treats all the road bars as similar objects. We evaluate the video imprinting performance on real-world videos for object removal and composed videos for background completion. The quantitative evaluation on the composed dataset shows that our method generates more accurate and temporal coherent video imprinting results than all the baselines and most of the existing methods. Finally, we show the comparison with the existing methods. Our method, while only trained on the input video alone using a simple 2D CNN, can generate video imprinting results that are better or as good as the methods that either use handcrafted image patch priors or priors learned from external image video corpus. Our method can employ better natural image priors to avoid shape distortions. When the input video contains significant lighting variance, our method still generates consistent results. Thank you.
Okay, so we have some short time for questions now. I first want to mention that all these videos are also going to appear in the website so that you can watch them in case anyone had some interruptions during the video. And you're welcome to ask questions in the Q&A spot that you have there. Maybe first I have a question regarding the in-painting, the last one. So I actually have two very quick questions. So the first one, have you considered combining the 3D architecture using 3D convolutions, but also combining it with the flow estimation?
Yes, for this question, we have tried that using combining these two together, and in our results, it doesn't show substantial improvements compared with the 2D CN, but using the 3D CN, it will making the time cost much higher. So we decided to only use the 2D CN.
Yeah, so in continuance to this answer, so how long does it take to train this network?
Yeah, so this is one of the drawbacks is the long training time of our method. Since for each of the input video, we have to train a model from scratch by mapping from the input random noise to the video statistics. So it usually takes 4 to 5 hours to train 1 minute video.
Thanks. So if any one of the panelists or from the attendees
I have a question actually to the second paper. So if I understand correctly, you train your network with patches, both from the single frame to the target frame you have, and you extract patches and like do all the training on patches, and then at test time you can inject full frames because your network is fully convolutional. My question is, why don't you do the loss function over the whole image at the first time, like during training? Why do you need to extract patches?
Yeah, thank you for this question. Yeah, so that's correct that we do the training on pages and then we do inference on whole images. And yeah, so we actually tried many methods. We tried many data augmentation methods because we are solving this problem where we have only one training sample because we have only one hand-painted image. And we tried many methods and nothing was working. So we tried to exploring this era, and we found that the explicit cropping of patches really works. So it's important to crop these patches explicitly. So even it's not intuitive because it's convolution network, it's fully convolution. So there are some patches anyways, right? So there are convolutions, and from the bottleneck layer, the network only sees some patches of the input frame. But still, it's really important to do this explicit cropping of patches. Okay, so I hope that answers your question.
Yes, thank you.
All right, so next we're going to have a keynote talk, and Michal will present our next speakers. Unmute yourself.
Yeah, can you hear me? Okay, so our next two speakers are going to give a joint talk, Tomer Michaeli and Tamar Shaham from the Technion. It's a real pleasure to have them. Tomer Michaeli, now an associate professor at the Technion, actually started his career in a totally different field, signal processing. He did a very impressive PhD, and I heard about him while he was still doing his PhD, and I convinced him to come do his postdoc at the Weizmann Institute, and while doing so, I converted him to computer vision. And I must say that having him as a postdoc was one of my wisest career decisions. And one of my biggest contributions to the field of computer vision was converting him to computer vision. So during his postdoc, Tomer and I developed a theory of how deviations from ideal patch recurrence can encode information about the unknown degradation of a single input image. This has led, Tomer's work has led to many follow-up PhD works, both at the Weizmann Institute as well as at the Technion, where Tomer is now a faculty. And Tamar Shaham is one of Tomer's excellent PhD students. She's now nearing her graduation. She did an amazing PhD, part of which you will hear about in the coming talk. And as I said, she's nearing graduation. And if you're looking for an excellent postdoc, then grab her if you manage to do so before I do that. In any case, I assume that many of you have already are familiar with some of their work, in particular with Tomer and Tamar's work together with Tali Dekel, and their beautiful work on SynGAN, which received the Mar Prize at the recent ECCV in Korea. So I'm sure we're going to hear both about that as well as other beautiful things they've both been doing in the past few years. So please, Tomer and Tamar, the stage is all yours.
Great, thanks for the introduction. So this is going to be a joint keynote. I'll give the first part of the talk and then I'll hand over to Tamar. And we're going to talk about several works that we did in recent years with the collaborators that you see at the bottom of the slide. And this talk is going to be about single image generative models. So learning the distribution or statistics of natural images is a fundamental task in computer vision. And when it comes to high resolution images, large images, this task is still considered to be very challenging because the diversity of objects and textures that we can encounter in an arbitrary high resolution image is actually huge. And there has been a lot of progress in generative models in recent years. For example, today we have large generative models like GAN that can generate these very photorealistic images. For example, these are draws from GAN from the class of market. But we should remember that the fact that our models can generate nice images does not yet imply that they captured the statistics of natural images. Because, for example, if we try to represent some image of our own with those models, like the image on the left, usually we get something that looks very different from the image that we targeted. So it's quite safe to say that even our largest generative models today can generate only a very tiny portion, maybe a negligible portion of the space of all natural images. And so a key question is, how do we move forward from here? And maybe before we answer this question, we should first be asking ourselves, why do we want to learn the statistics of natural images in the first place? And in many cases, the reason is because we have some particular image that we would like to manipulate, maybe in Paint or edit, and we need to employ some prior knowledge about how objects in natural images typically look like. But if that's our task, then in many cases, we already have a lot of training examples already within that particular image. For example, in that image, we already have many examples of apples, which are particularly relevant for that image. So we don't need another external data set of training sets of images, of apples. And more specifically, what I mean is, suppose that we extracted all the patches, all the overlapping patches from that image, and we somehow estimated the probability density function of patches in that image, then that density function tells us already a lot about the image. Now, of course, if we work with very large images and the patches are very small, then these patches do not tell us about global relations between objects in the scene. But we can also do this in multiple scales. And if we keep the patch size fixed, then the coarser the scale we go to, each patch covers a larger extent from the image. So over the last few years, we have worked quite a lot with this model. In this talk, we're going to tell you a bit about works that we did in the context of image editing and image manipulation. We also had other works in the context of image restoration, which we'll not mention here. So I'll start with the first work, which is which was done in collaboration with Tali Dekel, Michal, Irani, and Bill Freeman. And here, the idea was as follows. Suppose that I have some image, and let's assume for a minute that somehow I learned the distribution of patches in that image. We'll soon talk about how exactly we do this. What can we do with this distribution of patches? Well, one interesting thing that we can try to do is we can try to manipulate the image so as to control certain properties of the distribution. For example, we can try to deform the image so as to make the patch distribution have a lower entropy. Now, what does a lower entropy mean in the context of patches? It means that many patches are now going to be much more similar to other patches in the image. And if we try to do that, then we get a nice image that looks like that. And note that in the image on the right, every corn kernel is now much more similar to all other corn kernels. And also the rows are more nicely aligned. Now we can also go in the other direction. For example, we can try to increase the entropy of the patches. And what this does is it actually exaggerates tiny differences that exist between patches in the original image. So for example, here we had a slightly larger gap between the corn kernels, and this gap has been exaggerated. And here, for example, we had a slight deviation from a straight row, and this has been exaggerated. Now we can do this, of course, not only with geometric deformations, we can also do this with other types of transformations. For example, suppose we have this image here. We can try to look for a spatially varying color transformation, maybe a different color transformation per pixel, but the color transformation varies smoothly in the image, so as to increase the entropy of the patches in the image. And if we do that, then we exaggerate color differences between patches. So it turns out that in this image, although we can't really see it in the input image, the lizard is a tiny bit more bluish than the tree, which is a tiny bit more orangish than the lizard. Okay, so how do we do this? So the key idea is first to somehow represent the distribution of patches within the image. And for that, here we use perhaps the simplest method, which is kernel density estimation. So in kernel density estimation, the density of a candidate patch X is estimated according to the similarity of this patch to each and every other patch in the image Xi. Now, having an expression for the density function, we can also approximate the entropy of the distribution. And we get this expression, which it's quite easy to see that this expression becomes smaller when each patch Xj is very similar to many other patches Xi in the image. Okay, so we have an expression for the entropy of the patches in the image. Now we can formulate our optimization problem. And the problem is quite simple. What we would like to do is find some transformation T such that when we apply T on the image X, the entropy H of the resulting image would be small. And of course, in many cases, we would also like to require that the transformation T is regular, right? For example, if T is a flow field, then we would like to have some smoothness properties, and this is the second regularization. So I won't get into the details of how exactly we solve this optimization problem, but I'll just mention that because we want to capture statistics of patches at multiple scales, we solve this problem in pyramid structure. We start from the coarsest scale and get some initial guess for the next scale and so on until we reach the final scale. So let me show you a few examples of what we can do with this. Here is an image of a zebra with very strong patch recurrence. Actually, patches here recur along the stripes of the zebra. But the patch recurrence is not perfect, of course. And so what we can try to do is deform the image so as to decrease the entropy of the patches even more. So what we get when we do this is an image that looks like that. So it's very subtle. I'll flicker back and forth. This is the original image, and that's the corrected image. Okay, original image and the corrected image. Note how the curvature became smaller along the stripes. Now, if you want to see where exactly these small deviations from perfect recurrence occurred, then we can also exaggerate. And when we exaggerate the differences, we get this crazy zebra. And now you can see all the places where we had larger curvature than along the rest of the stripe. Here is another nice example. Here we have an image of a group called the Rockets, a group of dancers. And you can see that they're very nicely aligned, very evenly spaced, but even the Rockets are not perfect. So we can try to decrease the entropy of the patches in that image even more. And when we do that, we get an image that looks like that. So again, I'll flicker between them. That's the original image, and that's the nicely corrected image. So again, original image and corrected image. And note, for example, the girl on the right here, whose knee was slightly more bent than the others, and this was corrected. And the spacing between the girls on the left was corrected, and so on. And here is the fruit stand again. Again, here the boxes are very nicely aligned and the fruits within the boxes. But again, it's not perfect. If here we try to decrease the entropy, we get an image that looks like that. So again, that's the original image and that's the corrected image. Okay, original image and corrected image. And it's nice to see that even the bar at the bottom here was straightened because there are stronger patch repetitions along a straight bar. Okay. As I said before, we can do that not only with geometric deformations, but also with color transformations. And here we did a controlled experiment. We put 9 tomatoes, where 6 of which were bought a few days earlier than the other 3. So 6 of which are a bit riper than the others. But if you just look at the image, it's very hard to tell which ones are the riper ones. If we exaggerate the color differences, maybe increase the entropy in terms of color transformation, then we can clearly see that the 3 tomatoes here in the middle are the greener ones. They are exactly the 3 newer tomatoes, and the rest are the older ones. Now, what if we have more than one image? Suppose we have 2 views or multiple views of the same scene. So here, for example, we have 2 images of the Casa Miller building. We can extract 3D if we have 2 images. But now what if we want to correct these images or reduce the entropy in both images? Well, if we do this for each image independently, then we actually manage to remove the high curvatures in the balconies, but it's not done consistently, so the 3D reconstruction is ruined. What we can do is add another regularization term to our optimization problem, which encourages the 2 flow fields to be consistent with one another. I won't get into the details of how exactly we do this, but when we do this, we get this result. So that's the original pair of images, and that's the corrected pair of images. You see that the curvature was indeed reduced along the balconies, but we also maintain a good 3D reconstruction. Okay, so we saw that we can do various nice things with this multi-scale patch distributions, but one interesting question is, what exactly do these patch distributions capture? And to try to get some intuition, what we can do is a simple experiment. We can start with some image X, and then look for an image Y whose distribution of patches is as close as possible to X at multiple scales. How do we do this? We can start with some random guess, and then optimize over the image Y. Now, of course, the global optimum of this optimization problem is Y equals X. And believe it or not, in many cases, when we start with random noise, our algorithm finds this global optimum, or very close to the global optimum. But these are not the interesting cases. The more interesting cases are the cases where the algorithm converges to a local minimum. Why are those interesting? They're interesting because the loss for these local minima is also very, very low. So they have a very similar patch statistic, but they look different. So how do they look? Here is one local optimum that we got, and here are some other local optima. And what this shows is that our multi-scale patch distributions actually capture both local structures, like the colors on the balloons, and global structure, like sky at the top and ground at the bottom. Now, of course, here we used a very naive density estimation model, which is kernel density estimation. And the question is whether we can do better than that. We use more modern deep learning based approaches. And here I'll hand over to Tamar to tell you about.
Okay, thank you, Tamar. So yeah, it turns out that we can do better. And specifically in our last work at the ECCV 16, we introduced GAN, which is a powerful generative model that can be trained just from a single natural image. Now, given only a single training image, GAN is able to generate high quality, diverse image samples that carry the same semantic content as that image. Now, GAN is completely unconditional. It maps random noise into realistic image samples and does not require any object class label or external data. And this allows us to deal with general natural scenes. Once trained, GAN can produce arbitrary dimensions images, which semantically resemble the training image, just contain new object configuration and structures. Here, for example, you can see a new canopy layout and a new composition of birds. Now, training again on a single natural image was also explored by the group of Michal Irani, and they mainly showed it in the context of image retargeting. And here I'd like to show you many other tasks that we can do with our model. for example, super resolution, harmonizing an object into an image, editing an image, transferring a paint into a realistic image, and also producing a short video clips from just a single image. We solve all these tasks with the same model and without any further training or additional data. Again, with only a single training example. So how does it work? The key idea is to generate fake images with the same statistic of patches as the real image across multiple scales. To achieve this, we start with learning to generate the coarsest scale of the image. This is done adversarially with a patch discriminator, which attempts to classify each of the image patches as real or fake. Other than this adversarial loss, we also have a reconstruction loss that ensures there is a specific noise that will generate the real image of that scale. And this way, we actually ensure that the real image is included in our latent space. Now, once training is complete, we keep this generator fixed and move to learn to generate the next level. This only requires to add details on top of the generated images from the previous scale. Again, we use a patch discriminator and we minimize the same loss function. And we keep this process until we reach the final scale of the image. Now, all the discriminators and generators have the same lightweight architecture with a receptive field of 11 by 11, and therefore, they effectively capture structure of different sizes within the image. At inference time, we can generate images with arbitrary sizes by simply changing the dimension, the spatial dimension of the injected noise max. Now, we can train SynGAN with different number of levels. A model with only a small number of levels capture only textures. But as the number of levels increases, SynGAN is managed to capture also the global structure of the image and the arrangement of objects within the scene. Now, in practice, we always adjust the number of levels such that the effective receptive field at the coarsest scale will be about 40% of the short axis of the image. We also had a user study to quantify the realism of our images. We had a pair test and an unpaired test. And the confusion rate in both cases were relatively high, with the unpaired test nearing 50%, which is the ultimate score in this task. Now, the multi-scale architecture allows control over the generation. When starting the generation from the coarsest scale, we get highly varied samples. However, when starting the generation from the second coarsest scale, only finer details get modified. This is useful when the image contains one large silent object and we wish to keep its lowest structure intact. If, for example, when starting the generation from the coarsest scale, we got non-realistic zebra samples. However, when starting the generation from the second coarsest scale, only the zebra stripes get modified. Now, this ability to preserve the global structure of the image and to change only final details gives SynGANs the ability to solve many image manipulation tasks. Specifically, note what happened if instead of the training image, we would inject different image to the trained model. Now, SynGAN can generate only images which have the same patch statistic as the training image. Therefore, attributes from the training image are transferred into the injected image, causing an image-to-image translation effect, but with only a single example. Now, note that this task is challenging even for models like cycle GAN that were trained on thousands of examples. Okay, we can use this for many image manipulations. For example, we can train SYNGAN on this image of the mountains and then inject this paint. The result is a realistic image that contains the global structure of the paint, but the appearance of the training image. Another application is image editing. Here we simply copy and paste a few patches within the image. Now, SYNGAN tailor the pasted editing to create coherent and photorealistic image. As a comparison, Photoshop's content-aware move wasn't able to deal with this challenging edit. Another application is image harmonization. Here SYNGAN tailor the pasted object texture to match the background. Now note that this blending effect is different than other approaches, like this one by Luan et al., which impose color matching with the background. Now, the injection scale has a strong influence on the result. When the image is injected to a coarser scale, larger structures get modified. But as the image injected to a finer scales, only finer details get modified, and the global structure remains fixed. So the user can simply choose the desired effect. This is true for all applications. Another application is super resolution. Inherently, each of SYNGAN scales add content on top of the generated images from the previous scale. So imagine we could train SYNGAN on this low resolution image and then continue to upsample it using additional scales. Unfortunately, we don't have these scales because they correspond to image sizes that are larger than the training image. However, since the statistic of patches within natural images tend to be similar across scale, we can simply assume all the missing generators are equal to the last generator we have. Now, inputting this low resolution image to this extended pyramid, we get super resolution effect. Comparing to other super resolution approaches trained on a single image like deep image prior and zero-shot super resolution, SYNGAN produces much sharper reconstruction, which are actually similar in quality to SRGAN, although SRGAN was trained on thousands of examples. And we showed this in a quantitative evaluation we did in our paper, and you can check the paper for more details. An interesting property of our super resolution scheme is that instead of super resolving regular images, we can also super resolve random samples. Here, for example, we generate 4 megapixel random samples, which is a real challenge with unconditional GANs. Another application is image animation. Here we travel along SYNGAN's lattice space to produce smoothly varying video clips. We found that the most realistic effect is achieved by Gaussian random walk with momentum in the lattice space. So the effect is that these still images can be brought to life. Now, if you cannot see these videos in high quality because of Zoom, you can check out our website. Okay, so in the last year, we saw many follow-up works, and I'd like to show you some of them here. The first one is for diagnosing COVID-19 infection from a single radiological scan. Now, the motivation here is to train a detection network to detect COVID-19 infection in chest scan, but only from a single annotated chest scan. So what they did here is to take this single annotated chest scan and train a SYNGAN both on the scan itself and on the annotation jointly, and create random samples both of fake chest scans and their correct annotations. Now, taking this as the training set of a detection network, they managed to get really high accuracy. Another line of work is in the image-to-image translation task. We saw some of them in the short oral session earlier. One of them is TUIGAN, and they actually suggest to train two SYNGAN-like network in a cycle manner to create a single image-to-image translation effect, but with only a single unpair of pair images. And a similar approach was also proposed by Benaim et al. Now, Benaim et al. Also took SYNGAN into the video regime, and they extend it with a few levels of SYNGAN with a few levels of patch variational autoencoders, and show that they can generate random samples out of a single video only. Another super cool application is ToadGAN, where they took a single computer game level. This is Super Mario in this case. And they train a SYNGAN on the representation of this computer game to create random configuration of this level in different lengths and heights. Now, they also have a super cool GUI when you can upload the train generator, determine the size of the desired level, then start playing. Okay, so let's conclude. I hope we managed to convince you that there is usually a lot of information that can be extracted out of a single image only. We need to keep in mind that the idea of learning the internal statistic of patches within a single image has been around for more than 20 years, at least in the context of textures. Now, it will be very interesting to see how the community continues to explore this, not only in the context of image manipulation, but for many other tasks. So thank you, and we'll be happy to take any questions.
Thank you, Tamar and Tomer. As I said, beautiful work. I'm looking at the Q&A. I see there's a question by Yael Winkel. What are the limitations of the method when applied on conditional tasks such as paint to image or editing? For example, what if we would insert a paint with a red sky to a model that trained on a blue sky? Would that work? And another question, okay, Yael has two questions. Another question, what is the influence of the noise addition at the intermediate scales during training? So two separate questions, answer them at your convenient order.
Okay, so regarding the first question, so of course, if we have an image with completely different statistic and colors than the image we inject to the model, we will probably get very strange artifacts. But we can do some simple image histogram matching before injecting the target image into the model, and then we can translate the red sky into the blue sky, for example, do the image-to-image translation, and then transfer the histogram back. So if the problem is only with, for example, color matching, we can correct that before injecting the image into the model, and then we can avoid any artifact because of that. Tomer, would you like to take the second question?
Yeah, so what is the influence of noise? So noise is actually what gives us diversity. The noise at the first scale gives us diversity in terms of global arrangement of objects in the scene, like putting the balloons in different locations within the image. Noise at finer scales actually has a much smaller visual effect, but it does have some effect. Usually it's diversity in terms of the very fine details that you see on objects. So in each scale, we had to fill in some missing details, and we can do this with diversity. So the noise that we add adds diversity to the fine details that we add. But it's much weaker, a much weaker effect than the noise at the first scale, typically.
I don't have any, oh, there is another question. Oh, no, Yael just answered. Great, thank you very much. I don't see any other questions. Unfortunately, I don't have any questions because I know your work so well. I love it, but I know it bottom to top, left to right, so I don't have any additional questions. So if there are no additional questions from the audience, any of the other panelists, I guess we will move on to the third part of this session, and I'll hand it back to Assaf.
Thanks. Thank you, Tamar and Tomer.
Wait, there is another question here? No.
There's a question in
the chat.
Oh, okay. Oh, okay. I'm not handling this well enough. Sorry. Just a second.
So I can read the question.
Okay.
So the question is, for SYNGAN, it looks great. It produces very realistic output images. The visual results show the generated images are very similar to the input image. Two questions are here. One, are output images changed appearance statistics, lighting, texture, etc.? And two, are object shapes in the image changed as well?
Yeah, so because we are doing the training phase only on a single image, it can only generate information that was on that specific image. It cannot generate new information it didn't see before. So it can generate objects of different configuration and size and locations, but it cannot generate any new semantic context. For example, changing the lightning or something similar, because it has no notion of the semantic content of the image, similar to what we saw about the zebra generation. When we're starting the generation from the courses scale, we get highly varied structures of zebra with 5 legs and 2 heads. But if we start the generation from the second courses scale, we can keep the global structure intact. So I hope this answered the questions.
And I see there's one last question here. Thank you for a wonderful talk. Have you tried training SYNGAN with many images, i.e. on an external data set?
Actually, the architecture that we used has already been used before with a slight adjustment. So people have used similar architectures for external training. So the architecture itself is not new. The way we do the training is new. We do it layer-wise, scale-wise. So that hasn't been done in that context. But I think in terms of the architecture, yeah, you can do that, and people have been doing that.
Yeah, do you remember the name of the work?
I don't know.
It's a Gaussian pyramid GAN.
Laplacian pyramid.
Laplacian pyramid GAN.
Yeah, we have a citation in the paper, so you can find it.
I think we should move on. Assaf.
Great. Thanks, Tamar and Tomer. It was a really great talk. And we're now moving to our third oral session. This is a oral session about 3D. And please ask questions in the Q&A spot, and the presenters will answer these questions afterwards.
Good afternoon, everyone. I am Pallavi, and today I'll be talking about our work on depth completion using a view-constrained deep prior. This work was done in collaboration with University of Maryland and Microsoft Research. To understand the background behind our work, we refer the audience to the deep image prior paper that, given a corrupted image, predicts an uncorrupted image as close to the original as possible. They use the structure of the deep network as a natural image prior. They show the result of this technique on various applications like super resolution, denoising, inpainting, etc. We use the inpainting technique for depth maps. So, for deep depth prior, the inputs are RGB and depth images. We use an encoder-decoder network architecture like UNIT to produce completed depth maps using these inputs. The input to the encoder-decoder network is random noise. The output is a 4-channel RGBD output giving I out and D out. These outputs can be compared to reference, depth, and RGB inputs using reconstruction loss. Reconstruction loss can be L1, L2, SSIM loss, GAN loss, etc. We use a combination of L1 and SSIM loss. For more details, please refer to the paper. Finally, given depth map at reference viewpoint, we can warp the neighboring views into the reference view, giving the warped RGB image. This warped RGB can be compared to reference RGB using a combination of L1 and SSIM loss, which we will call as photoconsistency loss. This concludes our discussion on system overview. We will now talk about results on tanks and temples dataset. We use SGM and SFM to generate initial depth maps and camera pose for each video sequence respectively. DDP is used for depth completion or refinement on each depth maps. And finally, we use off-the-shelf algorithm Fusible to construct the 3D point clouds from these depth maps. The results are on the Ignatius video from Tanks and Temples dataset. The metric we use for comparison is F-score, which is the harmonic mean of precision and recall. We compare various networks and losses as an ablation study. The networks are UNIT and SkipNet, and the losses are depth-only RGBD and warping-based losses. As we can see here, combination of RGBD with warping loss gives the best performance. UNIT and SkipNet performances are similar. Next, we show the improvement by applying DDP on different input depth maps. We use both SGM and MVSNet-based input depth maps and fill up the holes in these depth maps using DDP. In both cases, we get an improvement using DDP. Next, we show qualitative results on our own data set. First, we have one input RGB frame from a certain viewpoint. Next, we have the 3D reconstruction based on SGM depth maps. Next, 3D reconstruction results from DDP completed SGM depth maps. Finally, 3D reconstruction based on MVSNet depth maps. As we can see here, DDP fills up the holes in SGM maps from the obscure regions behind the cushions, and DDP results are even better than the MVSNet based results. This is a second scene, a third one, and a fourth scene. In this scene, the reconstruction from DDP completed depth maps is better, which is visible through the characters in the word free on the truck. We now show some results on the NYU dataset. The first column is the input RGB frames. The second column is input depth maps with holes in them. The holes in the input depth maps get filled using cross bilateral filter in the third column and using DDP in the fourth column. The DDP-based depth completion results are better, as can be seen in the PSNR scores and removal of haziness in the completed regions present in column 3. Finally, we show results of warping RGB images from neighboring views to reference views using various depth maps. The first row is input RGB in reference view. The second row is the warping result from neighboring to reference view using SGM depth maps. The third row is the warping result from neighboring to reference view using DDP completed SGM depth maps. Almost all the holes in the second row get filled in the third using DDP technique. In conclusion, we have applied deep image prior idea for completion in depth maps, conducted ablation with different networks and losses such as depth versus RGBD versus warping, shown both quantitative and qualitative results on many data sets, And last but not the least, an important point to highlight is that DDP is based on deep learning on a single image involving test time optimization and is independent of training data distributions. For more details, please refer to our paper. Thank you.
We introduced multi-plane program induction with 3D box priors. In this paper, we studied two structures in nature images. First, the box architecture of scenes and subjects. And second, the regular program-like texture or patterns in these 2D planes. Given an input image, our goal is to induce a program-like scene representation that jointly models camera parameters, the 3D position and orientations of the planes, and a repeated structure on multi-2D planes, all from a single image. Such a holistic structured scene representation enables 3D-aware image editing operations, including painting missing pixels, extrapolating the image contents, and synthesizing new views. We propose a search-based algorithm guided by neural network detected visual cues to find the program that best explains the image. Take an image as input. We first apply neural VPS to detect the vanishing point, and LCNN to extract wireframe segments in the image. Next, we filter out wireframe segments that are too short in length or not point to the vanishing point. We call the remaining wireframe segments the valid wireframes, and use them to guide our search. In the second step, we enumerate all combinations of 4 wireframe segments from the valid wireframes and connect them to the vanishing point to get 4 rays. These 4 rays partition the image into 4 parts, which we treat as the segmentation of 4 planes. Based on the box structure assumption, these 4 rays can unambiguously determine the 3D position and surface normal of 4 planes. We use the inferred surface normal to rectify each plane, yielding a set of rectified images. For each rectified plane image, we enumerate all possible program candidates and find the one that best describes its regularity structure. Specifically, we design some self-similarity metrics to compute how well every program is explaining pixels on the corresponding plane, and use that as our loss to rank these program candidates. By summing up the loss of 4 planes, we get the overall regularity loss of the candidate box program. Please refer to our paper for details. Finally, we use this loss to rank all candidate box programs and choose the one with the lowest loss. With our box program representation, we can reconstruct the scene from a single image and tour in it. Here are some more results.
Okay, so we will now have the Q&A session. So let's see if there are. So, okay, so everyone is welcome to ask questions using the Q&A mechanism. So I guess in the meanwhile, I have one question for the second paper. And so my question is, how do you exactly define the space of possible programs?
Can you hear me?
Yes, yes, we hear
you. You mean how to define a program in 3D space, or?
I mean, okay, so the video said that you have this search algorithm to find a program that depicts best. So what is the space of all possible programs? How do you define it?
Oh, yeah. So we use the neural network to detect some visual cues and use that cues to guide our search. The cues like vanishing points or wireframes. So we use the vanishing point to filter the wireframes towards the vanishing point. And as I said in the video, the valid wireframes serves as the cues and it helps the search. So the search space is combinations of that wireframes, and for each four of them will forms a 3D box, and we will search all the box and find the best one with the programs that best explain the image.
Thanks. And I also have a question for the deep image part for depth estimation. So I saw that you're doing sort of depth in painting, and my question is, can you handle, maybe you can handle other degradations that happen to depth, for example, noisy depth, or maybe to super resolve the depth, like adding fine texture to the depth?
Yes, so we didn't exactly do the experiments on like extensive experiments on noisy and texture because there is not a lot of data available. Like we would have to manipulate the depth data. We had a lot of depth data with holes in them, so it was easy for us to do more experiments on them. But as the original DIP paper showed, it does work with super resolution noise removal. And but the loss, like the kind of optimization you do might have to vary a little bit. This optimization was specifically for in painting, like hole filling. We also thought that it might help to improve the overall nature of the depth maps. Like by nature, I mean, sometimes the original algorithm might make some mistakes, not any specific things like noise and in like holes, but there might just be mistakes in the algorithm that the algorithm is making. We thought that our technique, our loss where we do a multi-view consistency loss might actually help to improve that as well. And that was actually kind of rare. We didn't see a lot of improvement in that, but in certain situations it did help.
Okay, great. So thank you. And I can see
there are also questions in the Q&A.
So there's only one question in the Q&A, which is not relevant for this period.
Oh.
Okay.
Sorry.
Okay. So great. Thanks to all the speakers. So we're going to take our second break now, and we will reconvene in about 25 minutes actually, at 4:35 Glasgow time. So thank you everyone, and we'll see you shortly. Thank you.
So see you shortly. Thanks. And by the way, in the next session, we have two keynote speakers, John Barron and Alexei Efros, as well as 3 more short orals. So it's going to be an exciting session, and we hope you'll all join us back at 4:35. Thank you. Bye.
Okay, so welcome back, everyone. We will shortly start our third and last session of this live broadcasting. We will first have a short oral session and then 2 keynotes. I remind you all that you can ask questions in the Q&A panel. Just use the Q&A chat. And I guess we can start with the short orals.
Hi, my name is Rana Hanukkah, and today I'll be presenting our work, Point to Mesh, a self-prior for deformable meshes. We're interested in reconstructing a surface mesh from an input point cloud, which is a long-standing problem in computer graphics and computer vision. In this work, we present a method for reconstructing watertight meshes from point clouds, where the prior is defined by a convolutional neural network. Instead of explicitly specifying a prior, it is learned on the fly from a single input point cloud, without any pre-training. Starting with an input point cloud and an initial deformable mesh, a CNN iteratively deforms the mesh to shrink wrap the input point cloud. Specifically, the CNN weights are optimized to displace the vertices of the initial mesh such that it fits the input point cloud. This ensures that the reconstruction is watertight, which is a desirable property since real objects are solid. This is especially important for surface reconstruction, since the input may contain holes or regions with low density samples. We said we optimized the CNN weights to displace the vertices of the mesh, but why not just optimize the mesh vertices directly? Well, there are many valid solutions, and as it turns out, a direct optimization leads to an undesirable result. But if we optimize the CNN weights instead, their inductive bias acts as a powerful prior, which leads to favorable reconstructions. This approach learns from a single input point cloud. The premise is that shapes are not random. They contain strong self-correlations across multiple scales. The optimized CNN weights act as a prior, which is what we call the self-prior. The self-prior encodes the expected shape properties and leverages natural repetitions present within a single shape. Central to the self-prior is the global weight-sharing structure of a CNN. On the one hand, convolutions are applied locally to extract salient features. On the other, the same local kernels are utilized over the whole shape. Optimizing kernel weights globally across the entire shape inherently encourages local scale geometric self-repetition across the shape surface. So in this work, we leverage the inductive bias of neural networks to learn a self-prior for surface reconstruction. The network acts as a powerful prior in completing missing parts and removing outliers or noise. For example, reconstructing a mesh from a point cloud with missing regions using a smooth prior ignores the character of the global shape, whereas the self-prior learns a more plausible reconstruction. We start with some input point cloud, and then we use this to calculate an initial mesh. If we know the genus is 0, we can compute an initial mesh using the convex hull. For non-zero genus shapes, we can use other techniques. The initial mesh is used as an input to a CNN, which predicts vertex displacements and applies them to the initial mesh. The deformed mesh is then passed to a differential sampler, resulting in a sampled mesh. We calculate the distance between the sampled mesh and the input point cloud, which is used to update the CNN weights. We iteratively perform this update, where the deformed mesh in the next iteration should more closely approximate the input point cloud. The CNN used in this work is based off our earlier work, Mesh CNN. Consider the following example, with this input point cloud and corresponding initial mesh. When optimizing the CNN weights, the mesh enters this difficult second-order cavity. However, if we optimize the mesh vertices directly on the same exact objective, you can see that it becomes trapped in a local minima. So here we can see how the network behaves like a prior, and by encouraging self-similarity, it can avoid poor local minima. We used a real scanner to scan the 3D objects pictured above. It's a bit difficult to see, but there are many holes and low-density patches where the scanner failed to properly sample the surface. Yet, the reconstructions cover the surface well. We compared against existing techniques on the task of denoising, as well as the task of completing missing parts. Thanks a lot for listening. Our code and examples are online, and feel free to get in touch with me about any questions about this work or in general. Hi, my name is Rana Hanukkah, and together with Amir Hertz, we will be presenting our work, Deep Geometric Texture Synthesis. We're given a single 3D exemplar which contains some geometric texture. We would like to train a neural network that can automatically understand and then synthesize the exemplar's geometric texture. So when given a different shape, we could synthesize the geometric textures from the exemplar over the target shape. If we had a 2D displacement map, we could compute a parameterization of the 3D target surface onto the plane. The resulting textured model can be used to displace the vertices of the target shape in the normal direction, which results in a 3D texture. But we don't have a 2D displacement map. Instead, we're given a 3D exemplar model which has geometric textures ingrained in it. It is not represented as a 2D parameterization over a base shape, and it's not clear how to disentangle a 3D geometry into a base and 2D displacement map. In other words, the geometric texture is not provided explicitly and the statistics are unknown. Yet, we would still like to be able to automatically learn how to synthesize the unknown 3D geometric textures from the exemplar over arbitrary target shapes. And geometric textures can't always be represented as a simple displacement map over a base shape. For example, a 2D displacement map that moves geometry in the normal direction is rather limited, since it does not encode tangential movement. So, synthesizing a geometric texture over some target shape involves building geometric structures progressively by iteratively displacing vertices in all directions. So, for these reasons, we want to develop a technique that analyzes and synthesizes the geometric structures directly in 3D, without parameterization of the exemplar or target shape. We want to progressively build the geometric texture by iteratively adding incremental 3D displacements to some base shape. This involves iteratively displacing vertices of the base shape and increasing the resolution of the displaced result. The idea is to learn to synthesize the unknown geometric structures over the base shape in such a way that it can later be applied to some arbitrary, unseen target shape. Specifically, the target shape might have a different triangulation or genus than the training shape. The base shape can be obtained for generic shapes via mesh simplification, which gives a coarse approximation of the exemplar. We want to train a deep network to learn the geometric textures from a single exemplar shape. This might seem tricky since we don't have a large collection of shapes which all contain the same geometric texture. But there's actually a lot of self-repetitions in textures, where local neighborhoods contain similar statistics. The objective is to learn the unknown texture statistics from local triangular pouches. Starting with the base mesh, we learn deep features on the faces of the input triangulation, which is used to generate vertex displacements. The output is upsampled, or in other words, subdivided, before going to the next level generator, which displaces vertices. This is repeated until reaching the finest level in the series. This slide is important because it presents the gist of our approach. We train a series of generators which progressively add geometric detail to the evolving mesh. Specifically, our approach has 3 phases. In the first phase, we create multi-scale training data from the 3D exemplar offline. In the second phase, we use the multi-scale inputs as supervision to train a series of progressive generators. Once we finish training, we apply the series of multi-scale generators to unseen target shapes to synthesize geometric textures.
Now let's enjoy from some more interesting results. Here we train on the toes and bottom. And here we train on the Lisa. Here we synthesize the bubble texture. Experiment, we train our framework on the reference mesh on bottom right. We fed the generator with different inputs on left from low to high resolution. We're wishing you all health and safety.
Thanks.
Thanks.
Check out our code and data online.
Hi, my name is Jung So from Seoul National University. And in this video, I'm going to introduce our work, Meta Transfer Learning for Zero-Shot Super Resolution. Single image super resolution assumes such diversion model. We're given low-res image is from a latent high-res image by convolution with a blur kernel, followed by decimation with scaling factor S, and sometimes with noise corruption. Previous CNN-based methods, such as EDSR and RCAN, show outstanding performance based on large-scale external training dataset. They are trained based on self-supervised setting with no condition, mostly noise-free bicubic downsampling scenario. To boost performance, most of super-resolution CNNs adopt heavy architectures with extremely large number of parameters. CNN-based methods show outstanding performance on bicubic downsampling scenario. For example, this is the result of EDSR. However, when the test condition does not match with the training condition, they poorly perform, as shown in this illustration. Meanwhile, the zero-shot super-resolution is a different approach to exploit image-specific internal information, which learns the information from a single image. As an image contains its own specific information, sometimes it is better to exploit internal information, such as non-local recurrence, than external dataset. Zero-shot super-resolution requires both learning and inference at test time. Therefore, it is more flexible than previous CNNs. However, it has some limitations. It requires thousands of backpropagation gradient updates at test time, which requires huge amount of time to get a single super-resolved image. Moreover, it cannot fully exploit external dataset. To relieve the limitations of ZSSR, we propose meta-transfer learning for zero-shot super-resolution, which aims to find the generic initial point that is suitable for internal learning. We employ optimization-based meta-learning scheme to make the network quickly adapt to an image-specific condition. Our method mainly consists of 3 steps: large-scale training, meta-transfer learning, and meta-test. The first step is the large-scale training. From a random initial parameters, large-scale training is a simple supervised training based on bicubic degradation, where it learns efficient representation, thus ease and stabilize the meta-learning. The next step is the meta-transfer learning. We adopt model-agnostic meta-learning with several modifications to find the sensitive, transferable initial point of the parameter space, where a few gradient updates lead to a large performance improvements. We set different Gaussian blur kernels as different tasks for meta-learning. The last step is the meta-test. Once the model is trained, the model is now ready to quickly adapt to a specific test condition. The meta-test step is the self-supervised zero-shot super-resolution. Within a few gradient descent updates, the network quickly adapts to an image-specific condition. Now we analyze our MDSR. These plots show the PSNR improvements depend on the gradient descent updates. With the updates, our initial point shows the worst performance, even worse than the random initial parameters. But after one update, our method quickly adapts to an image-specific condition, shows the best results among comparisons. On the other hand, other methods slowly adapt to the condition. These are the visualizations of previous analysis. The initial point of our method shows inferior results with noisy patterns, but within one update, its improvement is quite considerable, while the pre-trained model shows minor improvements. We also analyze the complexity of our method. Our method requires a small number of parameters due to an image-specific CNN and also shows comparable time consumptions. This is the result for large scaling factors. As this image contains rich non-locally recurrent patterns, our method can super-resolve well, even for the large scaling factors. These are the experimental results. Our methods show comparable results in various environments. These are the visualizations. Thank you for listening.
Okay, thank you very much for all the presentations. And now we will have the presenters here to answer your questions. So please write your question in the Q&A chat. While we are waiting for questions, I'll say again that we will have all the short orals available in our website right after the second live broadcast of the workshop. And in the meantime, maybe I'll ask a few questions. So my first question is for the first presentation, Rana. My question is, so it seems like the network has some bias through smooth shapes. And my question is, what will happen if we will try to estimate something which is not smooth?
So, like, I guess the question is, what do you mean by not smooth? Like sharp corners and sharp features, things like that?
Yeah, for example, yeah.
Yeah, so I'm not sure if we showed like something. Actually, we did have in the presentation like this sphere with these kind of sharp rails that go around it. We didn't like pay particular attention to sharp features. We actually have like a follow-up work that's unpublished, which is dealing more with sharp features. But yeah.
Okay, great. Another question for the last presentation. So if I understand correctly, you used meta-learning in order to estimate the parameters of different zero-shot super resolution network according to the kernel, the kernel that it was blurred with before downsampling. My question is there any connection between parameters of networks that correspond to similar kernel in some way?
I haven't like analyzed about the similar kernels between similar kernels, but I'm not sure about that. Yeah, we just test on different kernels. I'm not sure about that.
Okay, but do you think that similar kernel will have like similar parameters?
Yeah, we try to like see what happens when the kernel mismatches, and we found that similar kernel shows much better results. So that means like I'm not sure about the parameter space, but I think they'll have similarity between like kernel. They'll have correlation between similarity in kernels and the parameter space. I think so.
So I have some questions, is that way? So first for Rana. So in images, we know that recurrence of patches, we know to quantify their size. Sometimes it's 5 by 5 patches or 7 by 7. And my question, what is the parallel when you look at meshes? So can you quantify it with, I don't know, the number of edges or the number of nodes that make this building block that tends to repeat?
Yeah, so on images, you have like a regular grid, right? So you have a 3 by 3 patch, and that's like a well-defined thing. In meshes, it's like an irregular structure. So we consider like local triangular patches by like looking at the rings of like, for example, if you look at a vertex or if you look at an edge, all of the neighbors that are coming out of that edge or coming out of that vertex would be the essentially like will define the receptive field. In the first, well, in both works we use some type of mesh convolution, which is working on edges or triangles.
Okay, and another question regarding this: did you also see recurrence across different scales? Do you have any feeling about it? So if I do, like you have in an older paper, you have this mesh pooling or edge pooling. So if you do this pooling and now you have this downsampled mesh, do you have repetition of information from the small one to the larger one?
Yeah, so that's a good question. I mean, geometry, at least like a lot of the geometric models that we look at, they don't have as much rich information as images, for example, which have like really clear texture scales, right? With the geometry, a lot of times the shape is a lot smoother. There's less small scale details. But I do think that even though shapes are sort of smoother than images for the most part, there is some like non-local information that is consistent across the shape. So yeah, I don't know if I have like a great intuition about like something like that, but that's like maybe what comes to mind.
Okay, great. And if we have time, I also have one question regarding the meta learning for super resolution. So as I understand it, the pre-training process eventually learns to get to a point where it would be good to fine-tune from, right? So my question is, did you in any way try to analyze what makes this point special? Like the filters make more sense. So why is it so different from just starting from random filters? And another thing, what makes the internal learning that follows, what makes it not to diverge too much and to do what we often bump into, which is catastrophic forgetting of the pre-training? We can't hear you. So we're getting no audio from you.
Oh, okay. So, actually, I'm not sure why it's like it happens. It acts like that, but our objective function, like we trained based on meta learning scheme, and this meta learning scheme objective function works to be transferable and sensitive to different kernels or different tasks, and that's how we train the network. So the network behaves like that, but I don't actually understand or like how it behaves like that. It's like kind of black box, and we just found that it works like that. And for the second question, you are asking about catastrophic forgetting about the method, and we found that just several gradient updates does not like affect that much of the information loss or like diverge, but we found that within several gradient updates, it's enough to like learn something new, not from the large data set. Yeah.
We actually have another question from the audience. The question is for meta-learning ZSSR. And the question is, generally, MZSR seems to outperform ZSSR except for the case of isotropic kernel with lambda equal 0.2. What might be the reasons?
Oh, I think that we trained the network with the lambda from 1 to, I'm not sure, but 1 to 5. So 0.2 lambda 0.2 is not in our training set. So I think that is why the performance is not as good as the ZSSR. I think that's the reason.
Okay, great, thank you. Thank you very much for all the presenters, and we'll move now to the next keynote. So our next keynote is by John Barron, who is, I think, here already. John is a staff research scientist at Google Research when he worked on computer vision and deep learning. He received many awards, including the Ramamurthy Distinguished Research Award in 2013 and the PAMI Young Research Award in 2020, and also the Honorable Best Paper Mention Award, both in ECCV 16 and also in this venue, ECCV 2020, so congratulations. John will talk about neural radiance field and how we can use it to represent a single 3D scene in a very efficient yet powerful way. So welcome, John.
Hi, thank you. Is my audio working? Can everyone hear me?
Yeah.
Okay, and I don't use Zoom very much because I work at Google. Is my slides are presenting and everything looks normal?
Yeah, everything looks perfect.
Okay, great. Well, thanks everyone at this workshop for the invitation, and I guess thanks to all the participants for coming and watching. I think this is going to be a little bit of a departure from some of the themes here, but there's going to be a lot of, I think, common ground that we can find in terms of representations for 3D world things. So I'm excited to see what we come up with. So I'm going to be presenting 3 things. First, I'm going to be covering NERF. This is a paper that was at ECCV this year, and it's made a pretty big splash. So I'm going to kind of cover it briefly and assume people have seen some of it. So on my screen right now, I'm seeing a beautiful animation of like a rotating vase. And I'm guessing that everyone else is seeing a kind of chunky, slow, heavily compressed video. Is that correct?
Actually, it's in pretty high quality, very surprisingly.
Oh, okay. Well, that's good. Well, so repeatedly throughout this talk, I'm going to claim that results look very nice and very good, and you'll have to take my word for it sometimes, I think. But I would encourage everyone to, if they haven't seen NERF results, to like open another tab and go check out the project page and look at the videos, because they're very nice, and you won't get a lot of that from this talk. So yeah, so I'll be reviewing NERF, and then I'm gonna be reviewing 2 follow-up papers that we have. So first, a kind of theory-oriented paper that we have online right now that it provides a theory for why NERF works, and also why a lot of implicit neural representations work. And then another more conventional follow-up that's kind of about extending NERF to work on a wider, more challenging set of scenes. So, so first, NERF. So this was at ECCV this year. NERF is an acronym for neural radiance fields. Neural because a neural network, field because these neural networks are kind of describing a continuous function in 3D space, so a field in like the calculus sense. And radiance in that these neural networks are describing a field of kind of glowing stuff, which you can think of as like radiance at a point. And this was a collaboration with between Berkeley and Google. And again, I would strongly recommend checking out the project website. So over here, we have the problem statement. So on the left, you should see a bunch of still images that are changing slowly. And on the right, you should see a smooth video. I'm not sure what you're seeing. But the problem we're looking at is, taking several images of the same scene and then recovering a model that allows us to generate new views of that scene with photorealistic quality. And I think we've achieved that goal. The results that we're getting from this model are basically photorealistic. You can find some small artifacts in kind of the periphery of the scene, but overall it's a really significant boost in quality for this task. And the model for this is very simple. There's a neural network. It has 9 layers and 256 channels. It's about 5 megabytes of weights. The input is 5 numbers. So X, Y, Z, where you are in space, and then theta phi, the viewing direction. So how you're looking at that point in space, where you're looking at it from. And the output is 4 numbers, RGB, so a color, and then a density, which is how dense that point in space is. And this is it. This is the whole model. This is going to, there's no training per se. This is kind of just more like using a neural network to memorize the scene. So all the properties of the scene are going to be stored in the weights of this neural network. Just once you've finished training, the way you would render an image from a trained NERF is using traditional volume rendering. So you define a camera and you take a pixel in that camera, you shoot a ray through it like you would in a normal ray tracer. And then you sample points along that ray. Each of those points is an XYZ coordinate in a viewing direction. That's common among the ray. You take each of those points and you feed them through a neural network. You can feed them all through together as like a batch. And then you get out, a few hundred colors and densities along that ray. You then just march backwards from the end of the ray and do alpha compositing from back to front. And when you're done, you get a color. And that's it. That's what it does. That's how it works. This is easy to train because if you read a paper from 1980 about volume rendering and implement it from the paper, you will discover that it all neatly slots into TensorFlow or PyTorch. Everything is trivially differentiable. Actually, a lot of things simplify to softmaxes and sigmoids and soft pluses, which is nice. So it's very straightforward to optimize. So we can train one of these models. And training is really kind of a misnomer. We can optimize one of these models from a set of images by just rendering the NERF and then minimizing squared error to the observation. And this decomposes into individual pixels. So we actually just make a training set of all the pixels in the scene, which all have a camera pose and array associated with them. And we just iterate through all of them, feed them through a very boring neural network and do gradient descent. And it works really well. This is a comparison against the state of the art for this sort of neural rendering task. This is SRNs from NeurIPS last year. And I'm not sure how clear this video is on your end, but on my end, SRNs produce a very blobby, kind of reasonable looking 3D model, but like definitely not something that looks like it is actually a photograph of the real world. And NERF looks basically like reality. So there's a very significant boost in quality here. And NERF has a lot of really nice side effects. One of them is that it actually has a very explicit 3D model of the world. Not really a 3D model. It has a very explicit volumetric density of the world baked into it. So you can do things like shoot rays at it and see where the rays terminate and get things like depth maps out of it. And so that's what we're showing here. And these depth maps, I think, are significantly better than what you're used to seeing from kind of multi-view stereo setups. There's none of that sort of blobbiness and over-smoothed quality that you might be used to. Lots of fine details and lots of sharp detail is visible. So what I just explained as NERF is a bit of a lie. That was an oversimplification of the model in one sense. The system I just described produces okay results, but not great. This is a result from the system, the kind of naive system I just described. And what you're hopefully seeing here is this fern, and it's slightly over smooth and looks kind of ghosty and not super realistic. And so during the course of this project, we discovered one weird trick that was necessary to get amazing results out of the system. And that was this positional encoding that we used. So to explain this idea, I'm just gonna kind of pull back to a very toy problem. So this is a really, really toy version of NERF, but I think even that's too charitable. This is a very, very toy neural network problem where you might wanna, you memorize a 2D image using a neural network. And this is something that's called a CPPN. This is the thing that it exists in the neural network literature as kind of like an oddity that you might do. It doesn't really have a purpose, but it's a very useful illustrative tool. So the goal here is you have a neural network that has two inputs, X and Y, and that's just the location of a pixel on a 2D image plane. And the output is RGB, and that's the color of that pixel. Surprisingly, this doesn't work. You can take a very, very large neural network and train it to do this, and it will fail catastrophically. So this is on the left, there's the image that we're training on, and in the middle is the neural network's reconstruction, and I'm just looping over the training. This is not a hard task, right? Like there's no generalization here. All it has to do is memorize the pixel values because it's seeing all the pixels. It just has to memorize them. And there's about, I think, 8 times as many neural network weights as there are pixels for this setup. And yet, despite neural networks being universal function approximators and everything, it just completely fails to recover the fine details of this image. It just kind of looks like this weird blobby polytopy sort of thing. This is super weird, right? Like this is a strange failure mode. You wouldn't expect this. The way we figured out how to solve this was to, instead of passing in the position as input, so the XY value, we instead pass in this is in the transformer literature, this is called a positional encoding. So this is, you take the sine and cosine of the values of your position, and then sine and cosine of twice that, and then 4 times that, etc. So you just kind of project each position onto a bunch of sinusoids with doubling frequencies at each level. So this is just a fixed function. It's just a fixed preprocessing step you do before you apply your neural network. It's about 1 line of Python. And if you do this, suddenly it just works. So on the right, hopefully you're seeing a perfect reconstruction of the image emerge very quickly. And in the middle, you're seeing a blobby weird thing. So this is super effective, almost bizarrely effective. And it's also very strange that not having it fails so badly. So the intuition that you might have developed for the 2D case just now, that extends or generalizes very well to the 3D case in NERF, and that's why NERF produces such nice images. And this really bothered us. We didn't understand this at all. And for a long time, we thought we couldn't write a paper about NERF because we didn't have a good explanation for why this was happening. And eventually we just punted and said, we'll just write a paper anyway. And it was a good call that we did that. But we just kind of glossed over this magical, important thing in the paper. And we immediately set to work trying to explain it to ourselves and to the community. And that led to this paper. This is up on arXiv now. There's a project page with some nice animated GIFs. So please check that out. It'll probably render more cleanly than this presentation. And this is one of those papers where the title is the takeaway. So Fourier features, which is what we're calling those projections onto sinusoids, or a lot of people call them that. They let neural networks learn high frequency functions, so functions with lots of high frequency variation in low dimensional domains. So if you have a task where there's a low dimensional input like X and Y, and you want to learn a high frequency function on those in that domain, Fourier features are the thing that enables you to do that. And this paper explains why. So here's just sorry, I'm having some Zoom difficulties here. Okay. Am I still presenting cleanly? Is everything looking okay?
Yeah.
All right. Yeah, just give me one moment to like manipulate some things on my end here. Okay. So here's kind of a cartoon visualization. Oh wait, are you seeing a video of talking heads at the top of the screen now?
We're not seeing any video.
Okay, on my end, Zoom is showing me myself where my slides used to be. So the slides look normal, nothing changed?
Yes, the slides look normal.
Okay, thanks. Thanks. Sorry, what was that?
I said no video on the slides.
Okay, great, thank you. Okay, so here's a cartoon visualization of what NERF is doing. You've got this input coordinate V, which is a very short vector. It's like length 5 or length 2 in the toy example. And then you feed that input vector into a fixed input mapping function, which we'll call gamma here. And for NERF, that was positional encoding, which I've written out the math for. So this takes V and projects it onto a bunch of axis-aligned sinusoids with frequencies that are just powers of 2 from each other. And it also lifts V up into a very high dimensional space, but that's kind of not as important as it might seem. Then you feed that positional encoding into a boring ReLU MLP, F, and you get the output, which is a single color and a density. So this positional encoding function has a single hyperparameter that we noticed was very important, this L value, it's circled in red. And this determines how many levels there are in positional encoding, how many scales. It also determines the highest frequency that's used by this positional encoding. And this was basically a knob that we could tune to regularize NERF. So if you set it too low, things would over smooth. If you set it too high, things would start to overfit, and you get noise and floaters and stuff in the results. So after staring at this for a while, we realized that positional encoding was just kind of the wrong thing to use, and that it was strictly better and cleaner to just use random Fourier features. So this is the math for that. We're just generating a big random skinny matrix B and projecting V onto it and pushing that projection through a sine and a cosine. This is a classic technique for kernel machines and straightforward discriminative learning tasks. And there's a lot of really nice work on these sorts of features that we were able to take advantage of. So Rahimi and Recht, NERPS 2007 is the classic citation for that. It's a great paper. Strongly recommend you check it out. So these random Fourier features also have this hyperparameter that's again shown in red there. And that's the standard deviation that you use to generate this matrix. And that has the same sort of purpose as the number of levels in the positional encoding. So you set it too high, too low, it smooths and overfits. Okay, so to understand what these Fourier features are doing, we found it extremely useful to bring in ideas from the neural tangent kernel literature. And for those of you who aren't familiar with this, the NTK is actually like a really remarkable result that shows that trained neural networks are basically equivalent to special kinds of kernel regression. So as a quick review, kernel regression is a classic nonlinear regression algorithm. And you can think of it as basically a way to produce output predictions by taking a weighted combination of the labels in your training data, where you use some predefined kernel function to measure the similarity between inputs, and then you just learn the weighting on those similarities. And And this is really surprising, but if you work hard and you squint and you stare at neural networks for a while, you can show that a fully trained neural network is technically equivalent to kernel regression. It's doing a kind of kernel regression. In practice, this isn't a super useful observation all the time because kernel regression can be very slow and hard to use because you need a matrix that has as many rows and columns as you have data points. So in our case, that would be a million by a million matrix because it's every pixel in the image. And then you need to invert that matrix. But we found this to be a super useful tool for just doing analysis to better understand how normal neural networks behave in practice. So another strange fact from the NTK literature is that for ReLU MLPs, the kernel that the neural network is implicitly using is a kind of dot product kernel. And that means that a ReLU MLP behaves very similarly to taking a dot product of its input with all of the training data and then pushing that single scalar dot product through a nonlinearity. When your input is high dimensional, this isn't that bad a kernel, as evidenced by neural networks being very effective across the board for many tests. But when your input is low dimensional, like in our case, you can kind of start to imagine why this would be problematic. If I was trying to interpolate into an image, for example, and all I had to work with were the dot products between the target pixel coordinate I'm interpolating and all the other coordinates in the image, I would have a really hard time designing an interpolation algorithm, right? That would be a very strange way to try to interpolate. And this is why almost anyone doing interpolation using classic signal processing techniques wouldn't do this. They would use like a stationary kernel, right? They would interpolate by saying, how far am I away from my other pixels, and then weighting them with some Gaussian or some tent kernel or something. So, okay, so now let's look at what dot products of Fourier feature mapped inputs look like. So here I'm just writing out the dot product from the definition. And if you apply a simple trig identity, you get this. And so you can see that the dot product of Fourier features of V is actually a stationary kernel with respect to V, meaning that it's shift invariant. It just depends on the distances between inputs rather than their dot product. This observation isn't new. It's been used a lot in prior work, just not for this task. So, okay, let's put those two pieces together, right? We know that our neural network is basically a kernel machine based around dot products of its input, and that the dot product of Fourier feature mapped inputs is a stationary kernel. So this means that composing a ReLU MLP with Fourier features gives us a new kind of neural network that corresponds to an NTK that is stationary. And it makes sense why this would be good, right? Because we know from signal processing that stationary kernels are basically just what you want to use when doing these, this kind of low dimensional interpolation task. And you can take this idea even further and notice that because our training data are densely and evenly distributed points in a low dimensional space, the output of this Fourier feature network is effectively a convolution with weighted deltas at each training point location. And this nicely parallels how you'd solve an interpolation problem using classic tools, right? You define some stationary kernel like bilinear interpolation or Gaussian or something, and then you convolve the input with that kernel to get a smooth and interpolated output. So basically, the very high level takeaway here is that this Fourier feature mapping trick is a way to turn MLPs into interpolating machines. So here's what that looks like in practice. This is the same 2D image memorization task I showed earlier, except here we have separate training sets and test sets of pixels. So we have to worry about overfitting, underfitting. We're only showing the model every other pixel, every other row and column. So this is like a 2x super resolution task. So here, we've got the output rendered for all pixels, training and test. And we've set the Fourier feature scale, that sigma value, to a particular value. It's about 4, it looks like. And you can see that the image on the left looks good. And on the right, you can see a 1D slice of the composed NTK that we now know that the model is basically using. So you can see that the kernel looks sensible. It's large at 0, and it's small, far from 0, and it falls off like Laplacian or a tent kernel, which makes sense. I mean, the support is maybe 5 or 10 pixels or something. And that's a very reasonable sort of kernel to use, and that's what our neural network is using, and that's why this is all working. So now here, we've set the scale parameter of the Fourier features to be very small. And this is similar to having no Fourier features at all. So just like you saw before, you can see that the output image from the network is heavily over-smoothed. And if you look at the kernel on the right, you can see that it's extremely wide. And this all makes sense because if you were trying to do interpolation with a very wide kernel, you'd expect very over-smooth results. And now we know that's exactly what's happening here. Okay, now here I've done the opposite, set the scale parameter of the Fourier features to be very large, and this produces a very noisy image, which you can see on the left. This might look less noisy for you depending on how the video compression is working. And in the middle, you can see the trained PSNR is very high and the test PSNR is very low, which is characteristic of this kind of overfitting we're seeing here. And on the right, you can see the kernel, which is way too narrow to be a reasonable interpolating kernel for this task. So looking at all this together, you can see that when you're using these Fourier features, the scale parameter of this fixed Fourier basis gives you a sort of knob that you can tune to, that lets you balance between underfitting and overfitting. And that this exactly corresponds to the NTK perspective on the problem where you have a stationary interpolating kernel that you're modifying the bandwidth of. That's what we're doing here. So at first we were just using this idea for NERF and it worked well, but we realized that we could basically apply the same sort of idea to a wide range of problems that you might see in computational imaging or 3D vision or things like that. So in all these setups, we just have a single scene or a single set of observations like pixels in an image or 3D occupancy, or even we did MRI scans and CT scans. You can try to solve these problems by training an implicit ReLU MLP representation on them, but it's heavily oversmoothed. This is not a very effective strategy. But for all of these tasks, you can just add in a Fourier feature mapping on the input, and then suddenly this really naive baseline of just trying to solve like MRI scanning or image super resolution by having a neural network memorize the input, this becomes really competitive, actually like surprisingly effective. So the image regression task comes into focus. We can now kind of super resolve. The 3D dragon gets a lot of detail there. And that MRI, you can now tell it's a brain. You couldn't tell it was a brain before. So this seems like a really useful tool in a wide variety of tasks. What's really nice is that it's super easy to try. This is what code looks like for a layer in a dense neural network as usual. And this is how you add Fourier features to it. So it's a 2-line change. If you're playing with these sorts of implicit neural representations, I definitely recommend giving this a shot. There are lots of contexts where it doesn't help. Like if you're in a high dimensional space, it probably won't help. But in lots of cases, it has an enormous effect. Okay, so that was a bit on how NERF works. And now I'm going to move on to an extension of NERF that's about making it kind of more useful. We call this project NERF in the wild because the goal was to get NERF to work on these sort of unstructured and uncontrolled photo collections you can grab off the internet. So in the wild is the buzzword there. This was a collaboration between Google Research and Google Brain in Berlin, actually. So NERF is very cool, but it has a very severe limitation, which is that it assumes, or really it requires that all the input images are perfectly well behaved. So no movement, no appearance changes, nothing. But we wanted to be able to apply NERF to kind of random flicker images of some scene. We use the Brandenburg gate here. And so that's how this project started. And as a side effect, the system that we came up with doesn't just let you move the camera like we could in NERF, but it also lets you change the appearance of the scene, like the time of day or the weather. So this in the wild task is really hard because internet photos of tourist landmarks are a mess. These images have likely been taken at different times, so the sun might move or lamps might turn on and off. And they could also have different kinds of post-processing applied to them, or they could just have been taken by very different kinds of cameras, which is its own big problem. So an even bigger problem is that people generally don't take photographs of landmarks by themselves. There might be people posing for the camera in front of the landmark, or pedestrians or cars moving through the scene, or flags and signs that might go up and down. So not only do we have to deal with factorizing the scene into geometry and appearance, we also have to factorize things into static and transient components, and then we want to remove those transient parts. So here's the architecture we came up with. It's kind of a wrapper around NERF. So the input to our system is just the location of a camera and an appearance embedding, which is just a vector in a low dimensional space. It's like a GLO vector, if you're familiar with that. And from these two inputs, we generate a static reconstruction of the scene, which is just the parts of the scene that are permanent, that are never going to change. We also generate a transient reconstruction of the scene that is specific to that one particular image. This reconstruction usually looks very poor, and it doesn't need to look good for our purposes. To generate the final image, we just composite the static and transient reconstructions together, and then this model is trained by minimizing reconstruction error against the target image from our data set, like in NERF. But for this to work, we also need to modulate that reconstruction loss according to an uncertainty field that's also generated by our model and is conditioned on this particular image. And this allows the training to ignore and identify transient parts of this particular image. So this is a cool extension of the NERF idea where there's this field, not just of color and stuff, but also of uncertainty, of basically like standard deviations, sigmas. And we alpha compose that down to an image. This lets the model learn things like stuff near the ground. I have no idea what's going on there because people are always walking through this part of the ground, which was very important. So after training, we can use our model to render novel views of the scene by giving it different viewpoints. Hopefully you saw the camera move there. But also by changing this appearance embeddings, we can change the appearance of the scene without changing the viewpoint or the scene geometry. So they're totally decoupled. So here's a fly-through video of that Brandenburg Gate scene. We're moving the camera, but not changing the appearance. This looks really cool. If it doesn't look really cool right now, go online, type in Nerf in the wild, and check out the videos, because these videos are really great. Here's a side-by-side with Nerf, which ends up hallucinating artifacts because it doesn't have a way to account for them. So a significant improvement there. Here's the Trevi fountain. You gotta use the Trevi fountain. This is, I think, a rule for this task, that you have to visualize the Trevi fountain at some point. And here's depth maps. We can get depth maps out the same way we did with normal Nerf, by seeing where rays terminate. Remember, our model isn't just recovering a single model of the scene. It's actually modeling the appearance of the scene in every individual image. So here we're rendering the scene with the same viewpoint, iterating through each of the different appearance vectors we recovered during training. You can see the structure and the geometry of the scene doesn't change at all, and that's because it's not changing. It can't change according to the architecture. These appearance vectors only affect color. So very nice separation of those two things. These appearance embeddings correspond, these appearances correspond to embeddings. We can interpolate between embeddings and do things like interpolate between times of day and different weather conditions, which is what we're doing here. I think these things look so cool. So if they don't look cool to you, try out the website. The comparison against the state-of-the-art neural rendering in the wild for this task. Again, I don't know what this looks like on your end, but on my end, ours is very stable, and neural rendering in the wild is a lot of temporal artifacts. And that's because it's fundamentally kind of an unstable approach, and Nerf is just this fixed density that is inherently stable. Here's another scene. We're just moving the camera. Again, these look really cool if they aren't compressed, so check out the website. And that's it. Thanks.
Thank you, John. Super interesting results. Thank you very much.
My pleasure.
So we have some question in the Q&A chat. Okay, I'll start with some of them. In the meantime, all the other participants are welcome to write us additional questions. So the first question is, what's your take on the generalization capabilities of the Fourier features? Should we try to use them as decoders for images and volumes instead of 2D, 3D convolutions?
Oh, I have no idea. That's a good question. I don't really think of, it's very hard to like take the part of your brain that thinks about generalization and apply it to these tasks because it's like such a weird fit. I can say that we have not seen any value in using these Fourier features in kind of normal ConvNet type tasks. That we've tried it on a couple, like, you know, you can imagine taking ChordConv or something and putting Fourier features on it. That in the few experiments we tried, that doesn't seem to work. But there was a paper at CVPR this year that did convolutions on sinusoids of positions. They called it like SineConv or something, and they got something out of it. So I don't know. I think that this result, this Fourier feature result, might be extremely important for a very narrow slice of problems, and then completely unimportant for other problems, because it really depends on this low dimensional issue. And for most cases, like ConvNets, the input is not low dimensional, like, because the input is the number of channels and the spatial support of your filter. So it could be this is just an oddity for this one corner case. I'm not sure though.
Okay, are the panelists also allowed to ask questions?
Sure.
May I ask a question?
Yes, Michal, go ahead.
First of all, very nice. I have a question. Could it be that this positional network, if you applied it to a Laplacian pyramid or to a Gaussian pyramid instead of just a single scale image, would actually solve the problem? Isn't this what you're actually doing when you're using the Fourier features? You're actually using multi-scale information. So wouldn't it be just solved if you did positional information in a Gaussian pyramid?
Yep, yeah. This project, that aspect of the project came about as first an investigation into using pyramids. I was very insistent that we would get something out of using wavelets or Laplacian pyramids and stuff. And you can think of these Fourier features as being kind of like, you know, a coordinate addressing scheme, like a pyramid-like coordinate addressing scheme. Like the core sinusoid is like, am I on the left side, the right side, and then you kind of zoom in through a pyramid. Pyramid stuff works roughly the same. So I don't know if one's better or worse, but the Fourier feature approach kind of has this redundancy built into it, or it's basically just like a more compact representation because you just encode the bits that get you down the pyramid rather than kind of the sparse location. But I do think there's a fundamental connection there to be made, and possibly also with deep image prior. We haven't made that yet, though. We don't totally know.
Thanks. Sorry for barging in. Go on, Tamar, with the Q&A.
That's okay. Okay, and another question. What would happen if you just project randomly to higher dimensions instead of using the cosine with double frequencies?
That's a great question. Nothing would happen because that's what the first layer of your neural network is already doing, right? Your first layer of your neural network is going from 5D to 256 or however many channels. And that superficially like lifts you into higher dimensional space because there's no nonlinearity and no sinusoid. It's the space, and it's a linear transformation, right? So you're actually still in a low dimensional space. You're just in a low dimensional subspace in a high dimensional space. So yeah, that's a good question. Yeah, there's something very special about the sinusoids there.
Great, we have a lot of questions. Did you measure the quality of depth of construction? What are the limitations of it? What is the minimal number of images for it?
Certainly like one image or two images are not enough. We're kind of comfortable in like the 50 to 100 to 1,000 range. That's kind of where we're at now. This model has never seen the world before, right? It's going into each scene fresh. So it has no prior beliefs about anything. So it's very much like an overfitting machine. So we need lots of data. Sorry, I feel like I skipped over the first half of the question.
What was the question again? Oh yeah. Yeah, I tried to pick the next one, and I got this question. Yeah, sorry.
Sorry, that's my mistake. I just got carried away with data.
Okay. Do we have time for additional questions, or should we move on to the next keynote?
We can take one more question and then move on to Alyosha. Unless you feel that your call.
Okay, additional question. Congratulations on winning the ECCV award. Fantastic results. I wonder about this positional encoding trick. Is it because you are transforming the position from discrete to continuous encoding, or because the deep NN are having issues with high frequencies? What is the source of the phenomena, and to what other tasks could it be used?
Yeah, so it's not about discrete or continuous, because the input is continuous, especially in NERF. The inputs are very continuous. They're all just floating points in space. The source of the phenomenon, as far as we can tell, is called spectral bias. That's a buzzword that's used in deep learning papers, and it refers to the idea that neural networks are biased to be smooth. We spent a lot of time reading papers that mention the phrase spectral bias, but it's really just a buzzword or a stand-in for an observation that people have noticed, and it doesn't actually doesn't terminate anywhere. Like there's no like a fundamental underlying principle there, or if there was, it was beyond us when we surveyed the literature. So neural networks are trying to be smooth, and in low dimensional spaces, that smoothness is very problematic. The NTK is the closest that I've been able to come to an intuition of like why this is happening. So you have to just kind of trust the NTK and then learn how kernel regression works, and then it starts to make more sense, I think. But this is all very mysterious, and being confused about it is totally understandable because we don't totally know either. Great.
Thank you very much, John. I feel like I need to thank you also personally, because for a while I tried to overfit a CPPM-like network to a single image and didn't manage to get it work. So now I understand why.
Cool. Yeah, now you can do it.
Yeah. Okay, Michal.
Yes. So our last speaker, Alyosha. Alyosha. What can I say about Alyosha? You know, I don't think there's a person in the computer vision community who doesn't know Alyosha. And no dry bio sketch that I will say about him will do him justice. So I'll give my own personal perspective of Alyosha instead. I first met Alyosha at ECCV 99. Alyosha was then, but probably many of you were not even born there then. Alyosha was then a young PhD student, just starting his PhD, and he was presenting his paper on non-parametric texture synthesis. And this work threw me off my feet. It was an amazing work. It used nearest neighbors of patches in images in order to synthesize more and more and more texture. And this is the first method to ever have, at least that I know, to have exploited the internal patch recurrence within a single natural image. And this formed the basis for much of the work that we know today on image completion, image denoising, non-local means, and so on. And it definitely completely changed the way I did research from that point on. So I don't think I'm exaggerating if I'm saying that Alyosha is the father of internal image statistics and internal learning. And it's impossible to have this workshop without Alyosha. So we're really, really glad to have Alyosha here. And it'll be a great dessert to have him give the final talk. His talk is titled Texture is from Mars and Structure is from Venus on Combining Internal and External Learning. So please, Alyosha.
Thank you for a wonderful introduction, Michal. First, I like to say how wonderful it is to be in this workshop with all my favorite people, and how sad it is that we can't go off for Scotch whiskey afterwards. But next year, hopefully.
Do, because I'm not too fond of Scotch and whiskey, but cognac is
okay,
good.
You know, we can also, yeah, sushi, whatever. But next year it will happen. And second of all, I also want to congratulate John on a wonderful work and a great talk as usual. So when Michal, and you know, of course, you always do what Michal tells you. And so when Michal tell me I should give a talk and I should talk about some of the old stuff, I said, okay, I'll try to kind of synthesize something that combines the old and the new. And so I've been worrying about this for the last couple of months. And so let's see if the synthesis works or not. Okay. So when I started my PhD with Jitendra Malik in late 90s, he told me to work on texture. And texture is it's not the most glamorous thing, I guess. It's a very special thing. It's kind of it's when you have a bunch of things in the image that are all kind of the same, but not quite the same. So you cannot really individuate them as this individual, radishes or pieces of rock. You kind of call them kind of as a joint kind of thing, texture of, a bunch of radishes, a bunch of rocks. But I have since realized that texture is really the microcosm of big data, and now everything I see looks like texture to me. And I'll try to explain to you why. So what is the magical thing about texture? What got me hooked initially? Well, it's the fact that you have something that could be very, very different in your standard, L1, L2 distance metrics. So here are some samples of texture that look very, very different on the pixel level from each other. And yet we humans look at it and we can see easily that this is the same stuff. How could this be? What are we doing? This is a very kind of fundamental, very interesting question. And this is, in fact, the question that first puzzled Bela Julish, who is really the father of texture, a great Hungarian psychologist. He was wondering exactly about this question. So you have somewhere, in the Platonic infinite texture that nobody has ever seen. What you're seeing, though, is you're seeing samples, some random samples from that Platonic texture. And somehow when people look at a pair of these samples, they're like, yeah, they are the same. So what is it that they then make them the same? What are some low-level statistics or some sort of, what are the sufficient statistics that allow humans to see that these two things are the same texture and maybe something else is different texture? And so this is kind of one of the Julish's experiments. He did a lot of texture experiments to show that sometimes we are very good at distinguishing different textures. For example, this thing is clearly different from the rest. And sometimes we're very bad at distinguishing textures, that things look like the same texture. For example, in this blue area, you can see that actually the stuff here are little T's as opposed to outside where there are little gammas. And it's very hard to see. In fact, I had to do this blue thing because otherwise you wouldn't be able to spot it. So it is, to humans, the same texture. And what Kulish was pointing out is that actually, these little crosses and these little T's, the same amount of ink and the same amount of, in the same number of strokes have been used for both of them, and yet you see these as two different textures. You see this one as the same texture. So there's a lot of really interesting psychophysical story here. And so Kulish developed this theory of textons, little texture elements, and trying to look at co-occurrences of them to model this phenomenon. And then people started thinking about, okay, what, instead of analysis, you can also think about synthesis. So for example, again, you have our infinite texture, and if you have some input image that is drawn from this unseen texture, can you use that input image to generate another one? Can you sample from that texture using this input image to generate a new image? Okay, and this is texture synthesis. So again, we need to kind of realize what is it that makes it the same texture? What are the kind of the statistical properties that need to be preserved here? Okay, and when I started working on this texture synthesis problem, I guess the thing that just made everything work out was this just very simple realization. I realized that an image is actually a data set, right? And a texture image, it contains a whole bunch of different things in it. So if you just treat an image not as a single sample, but as 100,000, say, sliding windows, then boom, everything just works out. Okay, and so then we just can use any kind of then it becomes machine learning. And what is the best, the simplest machine learning algorithm, Michal?
Nearest neighbor.
Thank you. Nearest neighbor, of course. And that's basically what our work with Thomas Leong was about. So we basically said, let's do texture synthesis using, essentially, make an n-gram, just like in text, unroll this n-gram onto pixels. Okay, so given that we have maybe already synthesized a bunch of pixels here, now we want to synthesize pixel P. How do we do this? Well, we assume a Markov property on images, and so we compute the probability of pixel P given the neighborhood of P, this thing, right? And so, in text, people just build explicit tables, probability tables. In images, it would be too much work to explicitly build those tables. So what we can do is we can do it online. We take our input image, and as we're synthesizing our output, we just sample, we do nearest neighbor in the input image, treating it as a data set, and just sample near similar neighborhoods from the input image and put it into our pixel T. Okay, and then basically the neighborhood window, the n-gram size, kind of nicely controls the kind of the context in all the natural ways that you've grown to know from text. And then, and it just produced good results. Look at this. It's not bad. It's so simple, such a brain dead algorithm. And it was just working very well. And it could do hole filling by just sampling from outside inward. It can do extrapolation from sampling inward to outside. Somehow, magically, it also worked for just regular images, not just for textures. People got excited about it. Michel Morel, according to AZ, saw this and got, oh my God, this is perfect for denoising. And so he basically used this idea to do denoising by taking a patch, and for every patch, just finding similar patches across the entire image, non-locally, and then just basically averaging them weighted by how close they are. And that, I think, is still considered one of the one of the best denoising methods, very simple, called non-local means. And so when I started my faculty job at CMU, I got a wonderful student, James Hayes, and one of the first things that we talked about, James was like, this is great. This is so cool that you can get so much from a single image. But surely you should be able to do even more if you had a database of images. Instead of one brick wall texture, if you gave it a whole bunch of them, shouldn't work way better, right? So let's try that. And I thought, this is a brilliant idea, James. This is fantastic. Let's do that. And so James, did a lot of engineering to kind of build up the system, and it was a complete disaster. It did not work at all. Not only it didn't help, it actually hurt performance. It was worse. It was much worse. And the single image performance, just very hard baseline to beat. So the question is why? And again, I will ask Michal, why do you think that is?
It's not fair to ask me. I'm already converted.
Okay. Well, it's basically because in a single image, a lot of the factors of variations that you would normally have in a data set are held constant just because of the virtue of the fact that it's somebody's taking a picture from a single point of view in a particular day, particular time of day, in particular GPS, and you're looking at a particular material, particular illumination, camera pose, exposure, color balance, blah, 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 blah. All of these things are held constant. So in a sense, it's an image is a data set, but it's a very nice and constrained data set. As soon as you try to inject more data in the data set, the problem becomes much harder because all of these parameters now start to vary. And so that is why things did not go so well for us initially, okay? And so this kind of leads me to kind of a fundamental conflict I see in trying to use machine learning for these kind of image synthesis, graphics tasks. So you have your input image, the image you're working on, and you want to use extra data, right? So you want to use other images to help you out. But then there is this conflict between how much do you use the image and how much you use the data set, right? If you use the data set too much, it stops looking like the input. If you don't use the data set enough, then basically just using the same input image, basically just doing internal learning, as Michal and folks have shown, is just good enough, right? You don't need the other data set. So what's that sweet spot? So one obvious thing one can do is just kind of go into the data set and only use the stuff that's close enough to what you are using or what you have, right? So you maybe just use only the zebra. So we did something like this, a very simple idea back a while ago with Jean-Francois Lalonde, where we wanted to insert objects and scenes. So we're trying to insert this car into this scene, and it doesn't look good. It just does not fit. And the reason it doesn't fit is because the car was actually taken from a nice clear day with blue skies, and here it's overcast. So your car is just too blue because it's reflecting the sky, right? And so what we said here is like, forget this. We can just find another image with another car that fits better. So let's match on things like illumination and geometry and find something that fits better. And now from stealing a car from this image, it just looks much better. So it's, again, we just kind of pick and choose what parts of the data we are going to use, okay? So that's definitely one way to do this, but it's kind of, unsatisfactory. You have this whole gazillion image data set, and you're only going to use like one thing from it. And also sometimes you don't want one thing. So for example, here, the texture we want from the zebra, but maybe the shape we want from a horse or something, right? So you want to somehow connect those two. So this to me is really kind of a fundamental problem that is hiding behind all of these things, including you know the like John's talk, for example, right? It's really that we need to do a disentanglement problem. We need to disentangle information that comes in inter-image across the images from the information that comes intra-image within the same image. Okay, so across the images, you're going to get something that basically captures the structure, captures the kind of the structure of the data. Okay, and within the image, you're going to capture something that we will call texture here. It's kind of a more generic version of the word texture, but I still like to call it texture because now to me everything looks like texture. If you listen to Josh Tenenbaum and Bill Freeman, you know, they call this style versus content. I'm not sure. I think the word style also has problems because it's been overused. So it's not quite clear what to call it, but there it is. So I'm going to talk about a couple of papers that we have basically tried to, you know, to push on this idea of disentanglement in this space. Okay. So the first one is a work that's was presented here in ECCV, and we are focusing here on just unpaired image translation, the same, you know, translating horses to zebras. You know, Tay decided to do the horse to zebra thing, and now you have to do it. So at this time, you're given a horse, and you need to basically make it as a zebra. So if you just do it naively, you take your horse and you train your GAN loss to make it look like a zebra. It could be any zebra. The GAN loss just says make it a zebra, but it doesn't necessarily has to be a corresponding zebra. So you have to have another constraint. And the constraint that we all usually use is cycle consistency, right? It basically, when we go back, it needs to go back to that same horse. And that kind of prevents it from kind of going and producing other things that shouldn't be there. But the problem with cycle consistency is it assumes a bijection. It assumes a one-to-one correspondence that maybe is not necessary. Maybe going from the zebra to a horse, you know, it's fine to go to any number of different horses. We shouldn't penalize these other horses. And so in this paper, what we try to do is to get away from this bijection constraint. And so the idea is that we want to kind of start from scratch, and we say, okay, let's do our image-to-image translation. Let's make this into a zebra. Okay, so we put a GAN loss to make it a zebra. Okay, but that's not enough. We need another constraint to make it a corresponding zebra. So how do we do this? By preserving the structure independent of the texture. So we're going to try to disentangle the structure and the texture by saying that these two corresponding patches of the input image and the output image, even though their texture is different, structurally, we want to bring them closer. They need to be similar to each other structurally compared to all these other patches that are not the same structure. Okay, and that's once we define this. Actually, doing this is not that hard. We can basically kind of just make the embedding of these patches be close in feature space between those two and far away from these two. And this is your standard contrastive loss story that is basically the same as a triplet loss story from before, but you know, works nicer. And so this is basically what we do, and it's kind of a nice way to kind of disentangle the texture from the structure on this patch level. Okay, and so. And we don't do it just on the pixels. We actually do it across multiple levels. So we have a multi-layer, you know, patch-wise contrastive loss. So it's multi-scale, and it you know, it works very nice. And here we gone away from doing any sort of like a metric. There is no L1. There is no perceptual loss, and we don't need to go back. So it enables a one-sided translation. Okay, and so one thing that we thought was, okay, again, the same thing as with James, you know, we're only using patches from the same image. Surely it should be even better if we add some external patches from other images, from other horses. But it turns out it actually, again, works worse. it works worse. Well, you know, obvious example is that if you by chance have kind of the same structure but different texture, you know, it kind of screws it up. But even if you don't do that, it works worse. So here is an example of translating labels to cityscapes, and this is internal and this is external. And you can see with external patches there is a bunch of places where it just mode collapses. Okay, so again, the same thing here. Internal is often better for doing this than using external. Okay, we also kind of can regularize it a little bit. So in addition to this kind of a loss that we talk about, we can also do kind of a regularize it with an identity loss by basically pushing it from doing zebra to zebra instead of horse to zebra, and just making sure that it's kind of does the same. And kind of this is a kind of a stabilization regularization thing. And so this is our method. We call it CUT, contrastive unpaired translation, and it's, you know, it basically kind of does what CycleGAN does but faster. And then we made a fast cut version, which is even faster. And here we forget about the identity loss regularization, just boost up the performance on the contrastive part, and it works even faster. And so here are some results of, you know, this is the speed of training, and we can see that we're doing quite a bit better and kind of on par with other one-sided methods. And here are the comparison with CycleGAN and comparisons to other methods as well. And the fast cut is kind of, you can see it's, you know, on par, but it's kind of closer to CycleGAN than the original cut method. And the reason it's closer is that it's interesting that, you know, there is some kind of an unexplained bias, unacknowledged bias. If you want to do horses to zebras, what we realized is that the zebras are actually much more zoomed in the data than the horses. There is much more zebra pixels than there are horse pixels in the data. And so, so if you want to translate it the right way, you should actually match these frequencies of pixels. But CycleGAN never did this because it wasn't able to change the structure. It was only doing changing the texture. And so what we found is that our method was actually more flexible, and it was able to match this distribution shift. And our zebras became fatter and, you know, healthier than the CycleGAN zebras. But sometimes that's not what you want. And the nice thing is that the cut model is actually much closer to what CycleGAN does. It does not do this kind of matching of this frequencies. It kind of does not let the GAN loss take over and do that. Okay. And of course, you know, we can do all the other cute little image-to-image translation-y kind of things. But another thing we could do is, with this method, is we could, you know, take inspiration from a lot of the wonderful work from this workshop, folks, and say we can do it for a single image. So we can map it to kind of image stylization. So we call it SimCut. So now let's say we want to translate from a picture of Claude Monet, painting of Claude Monet, to an image driven by a reference photograph of some water lilies. Okay, well, we can do this. We can start with basically a patch GAN discriminator, just like the other works, and on top of that, we're going to add our contrastive loss discriminator and combine those two together. Okay, that's basically it, and it just, you know, it seems to work pretty well. So here is some examples. This is a Modé picture of Etretat, and this is a Taesang picture of Etretat, I think. And you know, using that as a reference. So this is some of the previous works like Gatis, Strauss, a little bit better. WTC, it's supposed to be realistic, but it's not quite. And this is our result, which is, you know, pretty good. And for comparison, this is CycleGAN, but it's pretty good on the top, but then on the bottom it kind of screws up, whereas ours seems to be better. Okay. Here's our water lilies, the same thing. Gaddis, Strauss, WGCT. This is ours. This is CycleGAN. The lilies are bigger because again the kind of the matching thing didn't quite work. And here's some more examples for you. Okay. So here now we learn something that could be invariant to texture while preserving structure, but not really vice versa. So this is kind of a very specific, like image-to-image translation where structure is already fixed. Now, and we also have to rely on these domain labels. What is horse? What is zebra? So in the follow-up work, we thought, okay, let's see if we can address these issues and get something that's really trying to disentangle things kind of a more general way. So what we want kind of a true disentanglement of texture and structure. You can change one while keeping the other fixed. And we want these representation to be amenable to various downstream tasks. Okay. And so we thought, okay, let's just do an autoencoder. Let's encode an image, an input image, with some code and try to make that code disentangle, right? So here's our autoencoder. And our code, we're going to make this code separated into two parts. The code is going to have a structure part and a texture part. And the structure part is going to be kind of a retina topic. It's going to have the layout of the image. And the texture code is going to be kind of a global, just a vector for the entire image, okay? And the hope is that the autoencoder is just gonna split our data, disentangle it into these two things. Well, yeah, of course, it's not gonna do that. Why would it, right? If it's just an autoencoder. We need to convince it. We need something else, some other constraint. So that's why we make it a swapping autoencoder. So we then add another image, and then we want to swap in the structure from our first image while keeping the texture from this extra image to get something like this. Okay, so this is basically forcing it to try to make this disentanglement happen, right? So swapping is a pretext task to induce this kind of useful representation. But now, how do we make sure that this swapping task is actually doing the right thing, that it's not cheating, right? Well, we can put a GAN on it to make sure it still looks like a real image, but it's not forcing this texture to be the same as this texture. So for that, we basically go back to Ulish and say, okay, let's see if we can get something that kind of makes this thing that it's the same texture, right? So basically, let's do something that says, okay, these two patches should look the same. And basically, this is our straightforward adaptation of the Ulish. We take two patches, we encode it with a deep network, and then we have a MLP to basically train it to say the same or different. Basically, kind of a operationalizing Ulish and using that as a loss. Okay, so this is kind of the features, and this is like a co-occurrence of features. This is kind of your first or second order statistics that we all know and love from Ulish. Okay, so now we have our patch co-occurrence discriminator, and then we can give it a couple of patches, and it can tell us same or different. For this one, for example, obviously different. For this one, looks pretty same. This one, different. This one looks pretty same. Actually, it's not. It's different. But this one is a synthesized image that we synthesized based on the structure of this image and the texture of this. And it actually looks pretty neat. Okay. So this is our final story. This is our final swapping autoencoder. And then we basically just train it like crazy on lots and lots of data. And we can see how the swaps happen. So, if you don't do any swapping, it's basically just an autoencoder, everything's fine. But then as you start the swapping, you can see that actually it's doing kind of reasonable, cool things, changing texture without changing the structure. Okay, so here is some bedrooms for you, and you can see that it's kind of it's basically trying to steal the texture from the bed sheets and kind of populate it in there. And you can see that it's, it's mostly doing some reasonable things, okay? Without any supervision, really. We didn't tell it that these are, these are different domains, right? It's no labeling here. Here are some more examples, kind of texture structure swapping. But of course, what we want is we want this to be also used for something other things, some emergent capabilities, right? Not just swapping, but we want these things to be useful for something. And so here we have a kind of a GUI that Tae-Sang coded up to show that we can basically just go in and edit the structure code and, change the mountains for you. Or we can edit the texture code by, we just ran some PCA on the texture codes, kind of inspired by the GAN space paper of our friends here, and then use those PCA directions as buttons in this interface, and we can smoothly change the texture while preserving the structure and do various cool tricks. So here is some examples of just kind of walking along these PCA directions or in the texture space, and it's just changing the seasons and changing the lighting and things like this. Okay, and there is some more editing, but I'm gonna skip this. Here are some more examples of changing things. We can also do vectorial arithmetic. So, for example, we can take all the images at runtime. We can take all the images of summer hills, for example, average their feature together, and we can take all the images of mountains with snow, average them, and then we can just talk about like subtracting one vector from the other at runtime. So, for example, here is your input image, and this is input image plus that snow vector, and it adds snow to those input images. Or we can do subtraction. We can say minus snow. So there's an input again, and this is get rid of the snow. Okay. Okay. And we can do the same thing for portraits. So, for example, we train things on portraits and photographs, all at one big bucket. And then at runtime, we find the direction that goes from the portraits towards the photographs. And now we can basically do on-the-fly image-to-image translation to translate those make those portraits have the texture of real photographs by just pushing them in that direction, kind of vector, adding that realism vector to that. Okay. So in conclusion, learning for graphics can really be thought as a disentanglement problem, which is of course a very hard problem, but it seems like it's a necessary problem to take care of. It's separating this inter-image internal information from the inter-image, which is external information. And so what we showed is that for inter-image, which we would call texture, we showed that this patch co-occurrence discriminator can capture it independent of structure using these co-occurrences of unordered patches. And for inter-image, which is structure, we can use this patch-wise contrastive learning to capture the structure independent of texture. So these are the two papers. The code is online. Everything's online. Videos are online. These are my co-authors, especially have to mention Tae-Sang Park, the first author, wonderful student of mine, who has been the engine behind all of this. And thank you very much.
Thank you very much, Lyosha. Really amazing results.
Hi. Lyosha, what can I say? Every time I hear a talk by you, I always get envious. This is amazing. Amazing.
Michal, it's mutual. Me too.
Thank you. So let's see, we have two questions. We have several questions. Let me read out the questions in the Q&A. Are the patches selected in a sliding window fashion, or are they selected using some trick?
We don't have any trick at this point. So I guess in the kind of you could imagine I guess in the first part, that you can try to do some sort of hard negative mining and get more harder patches or something like this. We don't do any of this, but you can think of the contrastive formulation kind of does negative mining on its own. That's kind of that's a thing it does already. So the trick is in the contrast, that it's using it is kind of selecting the patches that are going to be helpful. But no, we don't do any of that ourselves.
Another question. So ideally speaking, using the extra external patches should have helped in learning the structure better. Could you zero it down why it went bad and why mode collapse happened?
So one reason why it could have gone wrong is if you have, as I showed, I think, okay, I'm not going to find this thing, but one reason would be that if you happen to have like the horse head in some other image, right? So you're trying to bring the horse heads together, but then you happen upon a horse head in some other image that you're trying to push away, whereas actually the structure is exactly the same, so you should be closer. That's kind of the wrong thing to do. So that's kind of one obvious example when you're just polluting your negatives with actually something that should be a positive. But frankly, I think that even if that doesn't happen, that's kind of rare things that could happen. But I think even if that doesn't happen, it's not clear why that is. I think it's the same story as why it didn't work for us with James Hayes all these years ago, that when you add external patches, you add all of this sort of different variations. So now you have patches that don't share the same imaging conditions. They don't share the same lighting. They don't share the same color. So they are not only unhelpful for this particular task. They're actually actively hurting you by aliasing to something that might be correct. So that's at least my theory for why this should not help, unless it's doing something very clever in doing this disentanglement. So like one could argue that maybe something like Pixel CNN or the Image GPT are doing this kind of disentanglement that allows them to kind of capture the structure kind of and be independent of texture. But frankly, looking at the results of the Pixel CNN and stuff, it's not really great. It's worse than our paper from '99. So I think that problem is still not quite solved.
May I add something before I read the next question? Even in non-local means, we found that non-local means is called non-local, but it's actually quite local. Okay, it's not totally non-local. It's doing it on a 30 by 30 window around the middle pixel or middle patch. It turns out that if you do non-local means and you exploit the entire space of patches in the image, it actually does worse.
Yeah.
Okay. And we found that the farther you go away from the patch, the less you have similarities. So you can think of this as a continuum. The local neighborhood of the patch, the entire image, the entire world, okay, of all the images. And the less certainty you have, which is the case when you have noise, the signal to noise ratio is very low, you want to stay local. When you have a good image and you do completion, you don't mind going global within the image, but you don't want to go externally because the camera that was used is different, the low pass filter that was used is different, the fog is different, and so on. So in that sense, we have this continuum. Sorry.
Right. Now, of course, if there was some oracle that told you, use the structure from this patch that is really far away and very different, but trust me, this is the right patch for you to use. If somebody were to tell you this, then it would be helpful. But that's itself is a super hard problem. Yeah, and if you don't have that oracle, then it's safer to stay close to yourself. Yeah, I agree completely.
So there's another question here in the, oh, wait, we have more questions in the Q&A. I see we have things also in the chat. Wait, blah, blah, blah. I think I read this one already. So did I read this? Wait a minute. For the contrastive learning work, how are positive and negative patches identified? How do you ensure that the patch from a different spatial location should be a negative patch? For instance, both patches can be from the background.
Right, so for the contrastive work, remember that we're doing the image-to-image translation task. So we actually have, we know what it should look like. We have the correspondence for free, right? The correspondence is given to us by the nature of the problem, right? We have the course and the zebra are in correspondence by, you know, basically just because we decided that it's, right? So that is why these patches, the blue patches, are given to us. They are in correspondence by construction, right? And the negative patches is just anything that's not the positive. It could be anywhere from the image. Okay, that's all. It's very simple, right? It's kind of usually when people talk about contrastive learning, they have to actually come up with, you know, what things are you know, the correspondences that are, you know, what things should be positive and what things should be negative. Here we don't have to, because our output is a synthesized image. It's not a real image. It's what we are creating ourselves. So it's up to us what it should be. And so we just, when we use it as a loss, it just gets us the correspondence for free. Okay, so that's kind of why normally this is a big problem in contrastive, and here we're kind of just skirting it because one of our images is our own synthesized output.
By the way, Alyosha, how big are those patches? Those yellow and blue patches that you're showing?
They are. I mean, they're multi-scale, so they're actually they actually happen inside of this encoder. So they actually in all multiple scales. They could be quite big. They're a whole range. I'm sure, you know, Tae-san can give you more details on this if he is here. But yeah.
Okay, we have another question. What could be the alternative approach to enforce internal similarity or texture as compared to the presented patch-based one, which requires hyperparameter tuning, number of patches, the size of the patch, and might be computationally heavy?
I guess this is for the second part. What would be the alternative? I'm not sure this is you know, this, where is this? The patch co-occurrence thing is not it's not that bad. I mean, you know, this is not so bad. I would think that this is actually pretty simple. I would claim that, you know, this is something that Yulish would have been proud of. You know, this is not a complicated thing, right? And the MLP is not very deep. It's actually quite shallow. It's not a hard problem. You know, people do texture in, like, you know, V2, V4. It's done. You know, it's very fast in humans. And so here you don't need that much processing. You know, pigeons can tell you Monet from Cézanne if you train them well enough, right? Texture discrimination is not a hard problem.
We have, I think, one last question, and I see it in the chat. Were you able to interpolate within the two disentangled spaces of the external images and internal images so far? So, for example, in the space of viewpoints, variations only present in external images? I'm not sure I understood the question.
Yeah, I think basically the question is, like, can we do the amazingly cool things that John Barron showed with, like, changing viewpoints? And the answer is no way. We definitely cannot do that. That is some magic stuff there. Now, of course, John got the viewpoints as inputs, right? So he basically, you know, he needs to have those viewpoints as inputs to do this magical stuff. We don't have that information. And I think it's really hard to discover it. Although I wonder if John can basically somehow, you know, push his system to kind of to find the viewpoints. I think that's the next frontier on that. But no, we're definitely, viewpoints are not something that we can deal with right now. It's definitely very much 2D story for now. But you can look at something like holoGAN, for example, as maybe one direction to look at that they're trying to do something like this. So holoGAN is also a very nice paper that I highly recommend.
Alyosha, this was a great talk, and I think this is the end of our workshop, a wonderful end of our workshop. I want to thank all my co-organizers and all the speakers in this workshop, and all the short orals as well, all the short oral speakers. I enjoyed this workshop very much. I learned a lot from it. And again, I think everything has been recorded. So the short orals have been pre-recorded and are up on our website. The keynote talks have been recorded live, and we will put them on our workshop website. And of course, even after ECCV, we will have our own workshop website. So even if you don't have access to ECCV, you will still have access to our personal workshop website. I don't know if any of my co-organizers want to add anything. I want to thank everyone. I really enjoyed this. Tomer, Tamar, Assaf, anybody?
I want to add just special thanks to Tamar, who was the leading organizer and did a wonderful job.
Indeed, yes. If it weren't for Tamar, we would all be lost.
My pleasure.
So, Alyosha, we must meet again at the conference.
Yes. See, normally this would be a time to go and get some sushi or something. And yes, now we just have to, get a cup of tea and yeah, so thank you for organizing this. Thank you, Michal. Thank you, Tamar, and everyone. And I hope that, next year in person.
Yes,
definitely.
Definitely. Bye-bye, everyone. Thank you very much. Bye-bye. Bye.